Hi everyone, and welcome to today's session. Today will be a continuation of last week's session on the hierarchical reasoning model. So this is a paper that actually excites me. In this few months, I haven't really seen anything that excites me as much as this model, because this model attempts to replicate some form of reasoning that might be present in the brain. They have a low-level processing module and a high-level processing module. And then this low and high level, interacts in such a way that the low level interacts with the data more often and gets updated more often, while the high level takes a backseat and gets updated once every like n time steps. And then at the end of it, the high level module will output like a hidden layer, which will then be used to give whatever output you want, be it the ARC-AGI grid, which is an IQ puzzle that you need to output like one of 10 colors in a grid. And also you can use it to solve like Sudoku and use it to solve maze exploration. So all these are typically not done with transformers, okay, or large language models, because LLMs or transformers typically do not do this kind of rule following very well, like algorithm following very well. But somehow this model manages to get it to do something quite remarkable. If you look at the results here, the results are quite good. Like HRM achieves a very competitive score, like 40.3% on ARC-AGI 1, about 5% on ARC-AGI 2. This is hard, by the way, ARC-AGI 2, where the pixels are not really pixels anymore. It's more abstract concepts. Like a square could represent like a certain concept in life, like a box or something. Right? So it's a bit different from ARC-AGI 1, where it's pattern matching. ARC-AGI 2 requires you to abstract into concepts. Okay, so Sudoku is amazing because it solves like 55%, while the rest of the like frontier models can't solve at all. Same thing for the maze, right? So how do they do this? So last week we actually covered on how reasoning is done, like not in the language form in this paper, but in the latent space. So I'll just do a brief recap, about 5 minutes of what we went through last week. Then we move on to the next part for this week. So basically, you don't express things like, hey, the cafeteria had 23 apples originally. They used 20 to make lunch. So they had 23 minus 20 equals to 3. They bought 6 more apples. So they have 3 plus 6 equals to 9. So, in recent times, we have discovered that just adding like a chain of thought step or reasoning step or like thinking step to the model, be it in like few shot prompting, where in the context, you already give it the reasoning examples, or by just queuing the model to output stuff like let's think step by step, can actually improve performance, especially for math problems where you need to break down the problem into steps. Okay, but there's a limit to this because the more steps you have, the more complicated the training is, and then you might, if you go out of sequence for your reasoning steps, you might get the wrong output. Sometimes the output doesn't even correspond with the thinking step or the reasoning step. So there are some issues with this. And so this paper asks, why not just do it in the latent space? Okay, this is also a sentiment echoed by like Yan LeCun, who says that, language is not enough for reasoning. So yes, instead of doing thoughts in language, why not do thoughts in latent space? And that's exactly the summary of this paper. We are thinking in latent space now. So I'll skip this comparison because we went through last week. So one thing is that by doing the thoughts in latent space, it actually scales better. Like it managed to scale the depth, like this is HRM, the blue color one. It scales much better than like a traditional transformer architecture. Okay, basically, because you are able to, pass in the information in latent space, is more efficient. You don't have to convert back to language. And so this leads to performance improvements. So this has correlations to the brain in terms of hierarchical, temporal, and recurrent processing. Right? So these are some of the examples of the tasks. On the left is ARC-AGI, which is like a kind of a logic puzzle. Here you need to match all these red color things to the squares, to the shapes. This is difficult. This is an optimization problem. You need to do it. There are easier problems like translating a square from left to right. Like you have a square here, and then you translate this to another square here. All right, then of course, you also have stuff like, Sudoku that you need to fill in the grid, and maze where you need to explore from the start to the end in one unique path, or rather the shortest path. Okay, so this kind of tasks are relatively difficult for large language models or transformers because you need everything to be correct. Transformers typically, you output the next token based on probability and so on. This basically makes it really, really hard because any token that is wrong will literally like invalidate the entire puzzle. Okay, so just a side note here. After looking at the code last week, I realized that the output for hierarchical reasoning model is not next token. So initially my understanding was because it's transformer architecture, you'll output this square first, followed by this square. So basically you give it maybe this entire grid. Let me just reiterate. Maybe you give it this entire grid here. You replace the blanks with like a symbol, like a dash. All right. And then given this entire grid, you output first cell first, and then second cell and third cell and fourth cell based on like, so I was thinking that, you output this cell condition on the input grid as well as whatever you have output before. Okay, this understanding turned out to be wrong, all right? So what exactly is it doing? It is taking this as input, this entire grid as input. Of course, this grid will be flattened into a one-dimensional grid because transformers don't take in 2D grids, they take in one-dimensional tokens. All right, so this, what one-dimensional sequence of tokens. So what this does is that you flatten this into like, into a series of like tokens like this, 8, 4, dash, dash, and then you do some processing whereby, something like that. You do something like this, and then you do a processing whereby, you convert them into token embeddings and so on. And after that, you go output the entire grid all at one go. All right. How is this done? After you pass this through the embedding layer, so you have an embed layer. Okay, let me just write this down. After you pass this through the embedding layer, then you pass this through the low and high module of HRM. So you do some processing in the low and high module. The outputs of your low and high module are actually vectors, hidden vectors. So you have a hidden vector. In the paper, it's a size 512. Okay, they didn't really put this in the paper, but I read through the code in detail. The size is 512. So it's impressive. A size of 512 can really do all this. Typically, I see in modern architectures is at least 1,000. Some even go to 2,000. Of course, we wouldn't know the size much because most of the top models are closed source, but the hidden vector size of 512 is considered quite small in recent architectures. So with this, then what they do is they feed through a final layer that maps into n by n grid output. So basically, the final layer will map at one go using this hidden vector. It will then get the output for cell 1, cell 2, cell 3, cell 4, cell 5, cell 6, all at the same time. Right? That was quite incredible for me because I always thought you will get better results if you do it like one token at a time. Because normally for large language models, you output like I am a, and the next step is I am a cat. The next is I am a cat sitting, and I am a cat sitting on, on the, and then I am a cat sitting on floor. Can you imagine if I were to ask you to output this entire sentence at one go from the beginning? What's the chance of error? Anyone want to like, maybe we just do a discussion here. Which is easier to get an error? Outputting the entire, okay, let's talk about the sentence. Outputting the entire sentence all at one time at the start, or outputting one by one here. Like you start with I, then after you do I am, then I am a cat. Which method is better for reliability? Like, do you do it one token at a time, or you do it all the tokens at the same time? Yeah, anyone? Like,
So clearly, like it both has its merits and demerits, right? So if you want to go careful one token at a time, so that's what your standard autoregressive transformer is. But like the diffusion models do, they try to take multiple stabs at giving the whole thing out. So this is a sequence to sequence model. So you expect it to try and attempt to solve the whole thing at once, but that's where you're forced to loop through and take multiple passes at it.
yes. So you take multiple passes to output the entire thing at one go. Sorry, to output the output in a diffusion model. But in a diffusion model, okay, for images, I think typically you output the whole image at one go. So maybe this is in line with that. But like for text, you normally output one token at a time. Yeah,
Correct.
so yeah, it depends on the domain, I guess. Yeah. I do think that In terms of reliability wise, it might be better to do one token at a time, just for conditioning. Yeah. So you can at least use the earlier information you have to guide it. Like for example, if you have this Sudoku grid, right? If let's say you output all these tokens here already, and you know the rules of the Sudoku, you already know that this is 3. Like so essentially you get a free information here just by outputting all these tokens here. Yeah. So if you output all at the same time, you may not know that, hey, my other branches are outputting 7, 8, 4, 1, 2, 5, 9, 6. You might output like 7. Yeah. But if you output one token at a time, you can condition on your earlier outputs and get a better answer. Yeah. So I think,
So
yeah.
also, John, like I think if you are doing the whole thing at a time, that's when you're forced to break the problem into a lower level and a higher level state, right? The H module cannot focus on the lower level details. So its queries, keys, and values will be like, hey, which part of the puzzle looks more solved, which is more constrained, which is, in the Sudoku example. So it can only do strategic things, and it's better off having the full picture at every point in time so that it can give the right kind of reset direction to the lower level module. So they're forced to bring in the hierarchy because it has to output the whole thing.
I understand. So for this high level and low level interaction in this part here, I agree you should pass the entire grid info at all the time. But what I'm thinking is that, for the final layer here, maybe instead of doing the whole grid output, the final layer here could just be next token.
Hmm.
Yeah. So then at the input level, so this is not in the HRM, but this is I think this might be better. So at this level here, the next grid cell information might be fed into the input again, like an autoregressive way. Like right now, HRM is not autoregressive. Like this information is not fed inside here again. But I'm thinking that if you can do this kind of autoregressive generation, it will make the output better. Yeah. So at least these are my thoughts. Okay, but let's take out this because this is not in the paper. The paper outputs the entire grid at one go. So I just want to highlight this thing here because this is quite a big difference from traditional transformer architectures in the sense of how they output the content. Okay, all clear for this? Yep. Derek?
100%. Yeah, yeah.
The low and high. So I understand better what you're trying to say earlier about the grid output. So the outer parts of the architecture where it reaches final layer, that's not what do you call it? Non-token based. It's not sequential at all. It's all output at once is what you meant. So it may be that not the recurrence, but the sequential tokenization may be unnecessary because the low and high modules are both respective transformer modules, aren't they? They're already transformers and I believe they still include the attention mechanism with the transformer modules from what I read
Yes,
from
they do.
they do keep that in the recurrent loop that they do. So it may be that maybe that from what their experience was in the early days when they were still building it out is that when they added the typical sequential architecture to the final layers, the outside layers of the architecture, and then also had transformer modules on the inner parts of the architecture. What they may have ran into may have been overcomplications in the token processing and generation pipeline. They may have found that they got much greater latency improvements by removing the complications altogether and just keeping the inner two modules attention based and then making the outer two modules simplified via just a basic hidden vector space or the other thing. I'm sorry, I didn't sleep last night, but you understand my point. Just removing the sequential generation altogether and having to do a direct input to output generation and keeping the inner two modules um, with the attention mechanism for the token generation.
Yeah, actually, it might be that this hidden vector is enough to represent all the cells already.
Right.
So maybe the condition checks could happen in the hidden vector for all you know. Because for me, I'm very used to the conditioning and constraints being done at the output layer, which is the language layer. Perhaps in this latent vector itself, it could already do those checks just by nature of, because when we do the loss function, we actually compare whether the final grid is it correct or not. We do an element-wise comparison, and then we can, fit the, like, hey, this cell is correct, this cell is not correct. So imagine if you have a loss function here that tells you, like, this is your cell 1 and cell 2. Let's, for simplicity, assume that there are only 2 cells output. So cell 1 output, and we have a cell 2 output. So already in your latent vector, for your cell 1 and cell 2 output, if you already can compare element-wise, like, this is correct, this is wrong, you can already say that, hey, in my hidden vector, hey, you better represent the cell 1 correctly. Yeah, because this is wrong. Like, if let's say in your hidden vector, I'm sorry, you want to say something? Okay, I'll be continuing, all right? So yeah. So basically, if let's say we output from the hidden vector to the final layer, and then you get a wrong output for cell 1, this actually can be reflected back to the hidden vector again. So what you say might be correct. The latent space might already contain the information needed to do the conditioning. I think that's what you're telling me, right, Derek?
Yeah, so the checks can be done either at, I remember what I was trying to say earlier, is feed forward. The final layer a feed forward, or is it is?
The final layer is like a linear layer where you transform the hidden vector. It's like MLP, like you take the hidden vector
Gotcha.
and then you go to the output size. So for example, in this case for a Sudoku grid, the hidden vector size will go into a 9 by 9 grid. In this case, it will just be treated as 81 neurons. All right, it's like 512 neurons. Like, this is your hidden vector, with each of these neurons containing, like, basically this is your hidden size of 512, and then you transform this into 81. Right? So this is like your linear layer, a linear layer of 512 neurons or 512 nodes to a linear layer of 81 nodes, for example. And each of these 81 nodes will have a vocab size of, like, in the Sudoku grid is 1 to 9. For the rest of the grid, it depends on the vocab. Like for ARC-AGI is 0 to 9 because they represent the black color as well as the other 9 colors. For the maze navigation, is either blank cell, black cell, start or go cell. Start or go cell. So there's 4 different vocab size if I remember correctly. Or actually there's 5 because you still need to have the path traverse. So it's 5 vocab cells. So basically, based on the problem that we have a certain vocab size which we map over here. Then you can do your softmax to extract out, like, to get a cell type. I call it cell type. Yeah. So this is essentially how the architecture works.
Gotcha. Okay, yeah. So, well, regardless of the actual architecture, so so pretty much it feeds forward through the vectors of the final layer. And well, what I think is that you could do it that way, but you also, from the internal processing of the low and high module, you should also already have checks during the gradient steps or during the processing of the recurrence between the two transformer modules, since you already have the low level one running it at its own frequency, and then it does the update with the high level one once it reaches a certain amount of steps, which I believe is what it's doing. And that already leads to kind of like learning to do checks already, just by the nature of the internal architecture of the low high module. So it's already doing processing in real time during the lane space, and it's already doing checks during its low steps and then high step update, and then back to low steps and then high step update. It's already kind of doing checks during that recurrent transformation and computation. So that's what I think. I think a lot of it has to do with that the low high module already has a lot of recurrence and a lot of checks already inside of it during its computation and during the recurrent high and low step switching and step updates. And I think a lot of that reduces the redundancy required of, say, doing a sequential layer or needing like attention or any more complex neural functions on the outside steps of the architecture of the pipeline. But
Yeah,
those are my thoughts. I'm open to input. I might be off.
No, I fully agree with what Derek is saying. Like they kept the important ideas of the attention blocks, the standard transformer module, which is the L module, the standard transformer, which is also the H module. But then they brought this beautiful loop around it, the RNN, and they preserved the state so that the L can be run t times, and then the H can be run n times. And there's also one more loop. There's the M segment, so that there's a consultant or this metacognition guy who's like watching the whiteboard and saying like, should we stop, should we continue,
Yeah.
because this is always problem solving, right? Because the transformer is not always problem solving, it's just writing, whereas this thing is specifically a reasoner. And it makes sense to bring in a third person who's just watching and saying, hey, how are we doing, are we really good to go, should we tell the loss function where we have reached. So I think it's phenomenal that they're bringing the loop into picture. So I think both the attention and the RNN's ability to kind of think longer, I think, is what's causing this to be such a market improvement with just 27 million parameters overall. So I'm blown away still. Like it's been a week, brainstorming with you guys and writing the blog post. But I mean, like, and just to clarify, right? The official ARC-AGI holdout set results are still not out. Am I right? And there's been some controversy. Maybe you can talk about it, John. But they responded. The team responded and said that the architecture is fascinating, and we're still trying to do it. And they themselves, our ARC-AGI team, is going to write a detailed post, it seems. And that's the
Yeah,
last thing
because
I heard.
actually to run this architecture, you kind of need to augment the training set. So like for example, everything at the top here is training. Let me just delete the whole thing. Everything at the top here is training. So what one thing that I will talk about also is that the HRM architecture, because it doesn't take in language at all, what it takes in is only this input grid. You kind of don't know, what the relation is. So it doesn't take in like context one, context two, it doesn't. So it treats all this as individual pipelines to run, and it only fits in the input grid. So what the pipeline for HRM sees is this grid here. It doesn't even know what the rule is. But in order to compensate for that, so I'll cover that in the later slide, but I think it's good to touch upon it now. We have a puzzle ID, puzzle embed, and then grid embed. So the input is both the puzzle embed and the grid embed. And you know what this puzzle embed does? Grid embed, you already know, like each cell gets converted based on its classification, the token here. It will get converted to an embedding layer, which is learned during the training process, how to represent each cell in the latent space. The puzzle embed represents the puzzle. So for example, this puzzle might be ID1, all right? So the puzzle might be ID1. And then this ID gets represented based on a lookup table. So it's like, how you do the lookup table for cell types. This is your ID. Your ID1 gets mapped into a 512 vector for your puzzle embedding. So the puzzle embedding is typically only one token. I look at the code. So each puzzle token gets embedded into a 512 vector, which will, this puzzle embed will be the first token of the entire thing. So it's like, every single hidden, every single basically input representation. So for example, if this grid here is like a 30 by 30 grid, so this puzzle embed equals to one cell, and the grid embed equals to, so there's a total of like 901 cells that are input here, because this is the puzzle embed is something like telling you what the puzzle is. So because there's no language saying that, hey, this is the input and this is the output. No, it doesn't work that way in HRM. HRM literally just takes in the input grid. So what you see in HRM is just basically this red, okay, maybe not red, this purple circle here. I'm going to draw a purple circle. So what the HRM sees is just this purple circle here, as well as, this ID. And actually for all this ID, for the same puzzle, the ID is the same. The ID is all one. Okay, so let me just readjust this. So it's a little confusing here because it's very different from how the transformer views it. If I were to use a transformer to do this, or rather LM to do this, I'll say this is my input, this is my output, this is my input 2, and this is my output 2. And now this is my input 3, what's my output? This is how I would do it in like a language-based transformer. But in this architecture, you're just taking in the grid as well as your puzzle ID. And then from there, you can come up with, because your puzzle ID will tell you like, I mean, literally the ID here is like, it's like your instruction for what to do. Okay, although this instruction is not in words, this instruction is in latent space. Is this 512 dimensional embedding that tells us what to do with this puzzle? So maybe in this embedding, maybe the instruction in this embedding is go and put all the red color pieces together. So like we won't know what it is because we can't see what's this embedding. But this puzzle embedding tells you what to do for the puzzle. And that's why if we want to do on the holdout set for ARC challenge, you kind of need to train this architecture on all the holdout set training data because only then you can get this ID. So when it's at test time, you can then just supply this ID one here so that, given this grid here, you can map to the output. So yeah, that's why I think for the ARC-AGI team, if you want to verify this model, they kind of need to train it themselves also. Right? There's no free lunch. You can't just take a trained model and use it on any puzzle because there's no human instruction at all. You are literally only giving it the input grid. Yeah. So I think I don't know whether that answers your question, Arvind, like how this is done.
Absolutely, and great explanation. Thank you for doing that. Yeah.
Okay, so this again is a limitation of HRM. Let me tell you why. Okay, personally, I've seen some up challenge puzzles, and not all the input-output relation is put in the same puzzle. Like for example, puzzle one. Okay, let me show you an example. Puzzle one might be doing this. Let me just delete the entire thing. Puzzle one might be doing this. This is puzzle one. Puzzle one shows you how a red square here gets mapped to maybe a red square here, like a symmetry on the x-axis. So maybe this is puzzle one, all right, input output sequence one. Okay, then maybe input output sequence two will show you something like this. If it's a triangle, then this will be like that. A symmetry in the x-axis. Yeah. So if you were to train on, let me just put here, if you were to train only on one input, you may not get the full relation, okay? Because the whole relation might be in all the input output examples. Okay, so I think this is a limitation of the HRM architecture because we are only given the input grid. We don't give like input output for all the context. We just give it only the input. For cases like this where the example is a little harder, the relation is not shown all in one go, there might be some constraints there because you kind of need to know how to do this across different IDs, like sorry, across different input grids. But I guess the funny thing about latent space is that if I give it the same puzzle ID, I don't know. I have to ask the team that did it. Like, are there examples of puzzles like this that their architecture can solve? Because that would be amazing. Because even without giving like input output for various contexts, I just train it on only the input across multiple examples. I can already get like both these rules, and then that would be amazing. So I think this is something that I'm not too sure about because like to me, just training on one input example and getting the output, even if you put the same puzzle ID, like it might be a little weird because like imagine if this relation is saying that, hey, it's a symmetry on the y-axis, such a simple thing, symmetry on the y-axis. But then your other training example is like, hey, it's a symmetry on the x-axis, it's such a simple thing. I don't know whether they'll be able to find out, hey, if it's a triangle, you flip on the x-axis. If it's a square, you flip on the y-axis. I'm not too sure whether this is easy to do. I think it's quite hard to do in this architecture. Whereas if I give you the complete picture at one go, maybe you can see the relations better because you can see the visual examples of all of them. So again, this is open for discussion. But I do think that there's some limitation with the way this HRM is, and it could be improved if we extend the input space that's given to the model. Yes, Arvind, you want to say something?
Yeah, a question. So, do you know how many data augmentations they do? Because I think they must be doing a lot.
They did a lot. I can explain some right now. So basically for the input grid here, they do some translation. So translation, I realize what it means because the input grid is always 30 by is always a certain size. So like this size can be maximum 30 by 30. So they actually can do padding of black squares. All right. So of course this padding here, as I said in the earlier example, this padding can actually, affect the symmetry and so on. So that they do some translation where they do padding, arbitrary padding on the this part here as well as the back here. And if I'm not wrong, for the test set they don't do any padding, but for the training set they do it to increase the number of samples. The other thing that they do is color mapping. So they change the colors, like blue becomes green, green becomes blue. So they have a few permutations. They random it. And again, you can also do rotation and you can do symmetry. So these are the rough augmentations that they do.
So, if I understand this conceptually, the number of inputs examples are only like 1,000 in the smaller data set, right? But then you augment it a lot, and each one of them you spend a lot of time thinking. You're looping through it like 3 nested loops, so that should give you a lot of training time, right? Like I think on a single GPU, I think they train for like a whole day for
Yeah.
ARC-AGI. For Sudoku, it's like 2 hours. So that shows that you are spending a lot of time during training, but it's just on each example you're taking a lot of time thinking through every state, as opposed to just taking a whole bunch of inputs and just running just once and merely getting a little bit of features and information out extracted. Right?
Yeah, so
Deep thinker.
there's some progressive learning here.
Yeah.
So like because you keep training on the examples, be it although it's like different examples, or you can also do a few epochs, so you can train on the same example again. The fact is, overtraining works in large language models, like in this case transformers. Overtraining works because when you learn stuff from earlier examples,
Yeah.
and you use that as your pre-trained weights and biases, you might learn even more things in the next few examples. Although it's the same example, but because you learn from other examples, you go back to the same example, you learn new insights. It is like humans also. Like maybe at
Correct.
first I don't understand the problem because I don't have the prerequisite knowledge. But once I train on other examples, I get my prerequisite knowledge from other examples, and oh, I see a new insight in this new puzzle. And I mean, in this old puzzle, it's the same old position, but I know new things now because I have new knowledge.
Correct. And there is enough bandwidth, enough weights, in the MLPs to store all the world knowledge. And in this case, that's absent. Yeah.
Yeah. So I think what you said makes sense.
So
But yeah.
one more thing, sorry to take this off. So this might be, they're saying neuroscience correlations. So even the brain might be doing it because we are also sample efficient. We don't do a task 1,000 times to learn it, right? With just 2, 3 examples, we're able to figure it out. But I think we do a lot of data augmentation, probably like this inside, right?
That's a possibility. Or either we do data augmentation or the latent space is so rich that once
Yeah.
you map into that latent space, automatically it can link to other similar things. So there are two ways to do it. One is augmentation at the input level. The other is if you have a good mapping into your latent space can tell you where are the similar ones, even without your augmentation.
I mean, man, this is so exciting. I can't even, express like what are we even talking about? Like we are getting closer every day. Yeah. Thank
Yeah,
you.
I mean, this might be closer to AGI than GPT-5, yes.
Seriously, yeah.
All
Yeah,
right,
I'll
so
let you continue. Yeah, thank you.
yep. Thanks so much for the discussion. I really enjoyed it. Yeah, so I think this is something that we need to bear in mind. Like, at what level should we do the input processing? Here, HRM opts for a very simple input processing pipeline, which may or may not be enough to process the complex data of the world. In this case, the world is the input-output grid. But like, if we talk about everyday life, maybe we can't just show one grid. We might need to show like a sequence of images for videos and so on. But that's for another discussion. So I'm saying that the input here is a little constrained for HRM, but with this constraint input, they solve quite a lot of problems. That's still amazing. All right. And before we move on to the math, the heavy math stuff, all right, I just want to highlight one more thing. Okay, what do you want to say? Okay, I can't remember what. Maybe I'll remember it later. Okay, let's just move on to the next part.
Was it about the Q learning part?
Oh no, it's not. It's something about the grid. But let me see whether I can recall it. All right. So yeah, this is the stuff that I was talking about. Like you have each example is prepended with a learnable special token that represents the puzzle, you know. So they do the variance, and yeah, basically what they do is they do some form of like mixture of experts in some or like what do you call it? The ensemble method. Like they just take 1,000 variants and they form a prediction. And this prediction gets inverse mapped. Okay, so what this means is like this. Okay, let's say if it's a problem that is a square that you want to, do a symmetry of the square. So maybe this is prediction one where the square is red. Okay, but instead of just doing a direct mapping, what I can do is I can do a mapping like this. I just use the bottom, right? I can map the square into a green square. And then maybe, my green square, in latent space, the green square is processed better than the red square. It gives you the correct relation. Okay, here my red square gives me the right relation also, but let's say my green square is better than red square. In my inverse map it back, I can get my red square here also. So there are different ways to solve a problem. You can map. So this is a transformation. And then this is the solve in transform space. And then this is the inverse transformation. And I think this does not just apply for HRM. I think this applies for any method that you have that you train it on like a fixed grid. Let's say if you want to do data augmentation, why not try this out in your method? You might perform better than HRM already. This is a very, very simple step to do for any kind of problem. You just do your variance if you have the idea of how a variant would look like. Solve in your variance space and map back here. You can also do this for math. You can map algebra into, polar coordinates and solve in polar coordinates and map back. Why not? Like IMO problems, you can do this as well. So I think this is a very good way to problem solve. In fact, we do this all the time in our heads. Sometimes we map a certain problem to in a different space and then we solve it. Yep. So yeah, this is the data augmentation that is now at test time. But at training time, you also do the same thing: rotation, flip, color permutation, and so on. And as I said, this translation is not done in test time, if I remember correctly. Because sometimes you might get the grade wrong if you do translations. Yeah. So this is something that is quite key. And yeah, you can also do the same augmentations for Sudoku and maze tasks, like by permuting the digits, right? And maze you can also, or maze you don't permute it, because maze there's nothing to permute, like the walls and the cells you can't permute anyway. Yeah. So this is quite interesting way to do data augmentation. And I just want to highlight something. The output grid size, based on what I saw in the code, the output grid size for ARC-AGI is always a 30 by 30 grid. And I guess they probably truncate it to the output grid. How they truncate, I'm not too sure. But the layer is always a 30 by 30. So yeah, maybe they truncate by black squares or something. Yeah, this is something that is quite, or they truncate to the input grid size. That's maybe another way. Yeah. So this is something that is potentially something that could be improved on, because if you only output a fixed grid size. Okay, for Sudoku and maze, I understand the fixed grid size is okay, because the Sudoku won't change size for the output, and the maze also won't change size for output as well. But for ARC-AGI, this is potentially a problem because you might truncate it wrongly. So I'm not too sure how they do this, because like I wasn't able to really identify this mechanism in the code. But the output grid being mapped to a fixed size is a limiting factor of HRM, if you ever think about it, because sometimes not all the output sizes are the same in real life domains. Okay, but I'm sure we can overcome this. Like you could have a way to, like what I mentioned earlier, do an autoregressive token prediction. Then that will be a dynamic size already, because you don't constrain to always having a fixed output grid size. Okay, but this is, if you're using HRM, this is one of the limiting factors, because it's not done in an autoregressive way. Okay, so use this only for tasks where the grid size doesn't change or the output size doesn't change. Like if you want to do sentiment analysis, maybe if you convert the tokens to language tokens, the output is always like positive or negative. Then HRM is fine. Okay, just to highlight this. And I remembered what I wanted to say earlier already. So, so the good thing about talking is you remember stuff. So I wanted to say that last week I was saying that, for all this ARC-AGI problems, the model is only trained on one task and then it trained really well. So let me just highlight. Okay, this is my understanding last week. Last week, my understanding was for ARC-AGI, one model for each task. Okay, but this week, with better understanding, for ARC-AGI, train on all tasks, but have a puzzle ID to tell which task it is. Okay, so this is something that I'm more agreeable to actually. Like last week, I was thinking that, because of the data augmentations, you only do it for one task each. But no. Actually, I look at the training code, you train on all the tasks. So this is actually better, I think, because by training on all the tasks, at least you might know how to do certain things like translation, rotation, symmetry from other tasks. And then, although it's a different puzzle embed, having the skills that you already have inside your weights and biases, you already have the skills for doing rotation, symmetry, and so on. It might be easier to solve a new puzzle, although it's a different ID. But your action space, you already know some idea of what to do, right? So this is what I wanted to say. I think the remarkable thing is that I've been trying to do all this ARC-AGI stuff like the action space in terms of like Python code, in terms of external stuff. A lot of people are trying to do in terms of external chain of thought, like in language. I should rotate the grid first, and I should map the grid cells from blue to green. Then after that, they do the transformer to do the LM to do the input to output like that, to output the grid directly in language space. But what this paper tells us, the HRM paper tells us, is that you can do everything in latent space. And it works even better than language space. So it's a fundamental rethink of how we are doing thinking. Like you can literally think in a space that you can observe, and it's better.
Yeah, I think it's going back to how the brains do. Like a lot of thinking is silent and inner thinking, as opposed to thinking out loud on a whiteboard, like the COT way of doing things in token space.
Very impressive. Very impressive. Yeah. So yeah, I want to highlight all this here because like new understanding. So I'm also not perfect. So I got an incorrect representation based on reading the paper. I also want to highlight something here. What the paper says is only 20% of what the code says. So some things in the paper are also not the same as the code. So I encourage everyone, if you want to get a good understanding of this paper, look at the code in detail. I actually use GPT-5 a lot to look at the code. I just copy paste the code in, then I ask GPT to explain what's going on, then I can ask questions. So I think you can do something like that. I mean, if you're interested, I also can put the chat that I asked GPT to do it. Yeah, so it's a really, the code is not easy to understand. Yeah, because some parts of it doesn't follow what the paper says, like the Q learning part. Later I'll explain why. But it was very insightful and it was a great learning experience for me because now I understand this architecture very well. All right, or at least better than I did last week. Okay, so this visualizing intermediate steps again, just for people who didn't really know, like every time step of the HRM model, you can actually take your hidden layer at the last layer and you can output back into the grid, and then you can do your loss comparison of your grid to see like which cells are output wrongly, and then you can feed back this information back into the hidden state and so on. So every time step, you have a training opportunity to compare with the model answer here. Okay, here we assume it's the model answer because like although this is the test time inference, but the last step is correct. I mean, they only show the correct examples. So like you can already have at every time step, you already have a training signal to tell you how far off you are from the model answer. And so this is like a constant teacher supervision to say that, hey, this answer is a bit off, modify a bit. This part of the maze is a bit off. This should not be, this should be eliminated. And then eventually at maybe time step 5, you see they eliminated the wrong part. So there's always a teacher student kind of learning at every time step. And this teacher student learning at every time step is called deep supervision. Okay, so we will cover this in the math. And I think I better move on to the math. If not, we will run out of time. So now this part 2. But don't worry, whatever we discussed earlier just now, some of it was part 2 already. In fact, most of it was part 2 already. So we are not exactly losing time here. Okay, so this is the main architecture that I need everyone to follow. So we talk about input layer, which again, we have seen that it's not just the grid, it's a puzzle embedding and a sequence embedding. So the puzzle embedding is typically the puzzle embed is is like 1 token. And then your sequence embedding or ARC-AGI is like 30 by 30 tokens. Right? It could be more or less depending on what size the input is. Okay, but the output is usually only 30 by 30. Like they have a fixed output size. So I just want to emphasize a bit on this L module and H module. So the L module here, what this module does, okay, so let me just put here. So the modules, all right, the L or H modules is exactly the same, all right? There's no difference between the L and the H module. The only difference in the L and the H module is the inputs. Okay, so what is the output for the L and H module? Very, very simple. The L and H module output is a hidden vector. All right, but what's the input for my L and H module? So the input for my L and H module is a mixture of this. It could be the input layer. It could be my L layer. It could be my H layer. So depending on the L module or H module, you get different things. So L module will take in the high, low, and the input layer. So it has all three inputs. The H module will only take in the high and the low without the input. Right? So this input layer is only for high. But if you look at it, it's exactly the same module. That's L and H modules exactly the same. Difference maybe is the backprop for H module is done separately to the L module. So the H and L module are not shared in terms of weights and biases. They are different. But the way the H and L module works is exactly the same. So look at the config file. It's like 4 transformer layers. And I mean, you can increase the layers. The config file probably, let's not put it because probably for our AGI, they use more. Okay. But same transformer layers. And what this does is that it passes in through the there's a self-attention here in the module. And then there's also basically a unity flow, which means that like it's like REST nets where you can actually pass in the input itself. So each of this self-attention in each of these modules, this is my L and H module. My input will go in here. It will go through the attention layer. And then there's a norm layer. I'll omit the norm layer. So there's an attention layer, and there's a unity flow here like that. Then we also have an MLP layer, multi-layer perceptron layer. Yeah, and then we have a skip connection here as well. So then this will form the output. So essentially, this is pretty much a transformer layer, and then you stack like maybe 4 of these layers together. So this is a transformer layer. Yeah, so it's similar to an encoder-only transformer. The L and H module are exactly the same. Of course, if you implement it your own way, your L and H module might be different. Maybe you want to stack more thinking modules in the H layer, stack more transformer layers, up to you. Okay. But the idea is that given an input, which is in the form of an embedding, you transform it to an output, which is also in the form of an embedding. And the input and output embedding is the same dimension. So let's pause here for a while to appreciate the beauty of this architecture. By having the input and output in the same dimension, what does this allow us to do? Anyone? What's the beauty of having the embedding layer in the same dimension? Okay, so I give you a hint, all right? It enables recursion. All right, it enables recursion. So can you see that in this architecture here, the L module fits back to itself? The H module fits back to the L module. All these are only possible, and also the input module fits to the L module, and the high level fits to the L module. All these are only possible because we have the same kind of vector space. And if I remember correctly in the code, the high, low, and the input, they are all averaged out when they process inside this module. So whenever you process things, you get a good dose of your high-level guidance, a good dose of your low-level guidance, as well as your input guidance for the L module. And for a high module, you have a good dose of a high and low-level guidance. So you view this hidden vector as guidance. It's something like, some language to tell you, oh, change red cells to green cells. Like something like that. The instructions might be inside here. And of course, the instructions might also be in the input layer because the input layer has a token that basically, is the token for the puzzle embed. So the input and output embeddings are the same dimension, but how many tokens do they output? Guess what? They output puzzle embed plus sequence embed. So basically the input token is so it's a little confusing here because this is a bit different from a transformer autoregression. At every single layer in your L and H module, I have a sequence of this. So maybe let me just draw this as a vector, right? This vector looks like this purple vector, and then this is your puzzle embed. Let's just make this puzzle embed a darkened part. So this is my puzzle embed, and this is my sequence embed, and each of this is 512 dimensions. So at every output layer here is essentially this structure. Okay, so you can add them together. Yeah, and that's essentially how they do the guidance from H, L, and input is all by adding these vectors together. And so at the final layer for your H module is also this vector where there's a puzzle embed here. So this is the critical part of the HRM architecture, right? Question, do you want your output here to be based on your puzzle embed? Anyone? The output for your grid, do you want it to be based on the puzzle embed? Yes or no?
Yeah,
you
of
can
course, right? Yeah.
Okay, so guess what? In this architecture, it is a no, right? We basically take away the puzzle embed. So what we do for the output layer is that this part here is your grid sequence, will then be fed into your output head, and then it goes to output. So this is your output dimension. Yeah, this is your grid dimension.
See, in the ideal case, you would want that to come back like even a bigger loop, right? But we don't have that here, so we just output the output sequence, the so that you can send it to the loss function.
Yeah. So over here, they did an intentional step of removing the puzzle embed. And I think it really depends on how you want to view it. Like it might say that, oh, this might be your, in your chain of thought reasoning, this is your chain of thought. Like you can view let me just write this here because it's a very important point. Your puzzle embed can be like chain of thought. Why? Because essentially your puzzle ID tells you like sort of the instructions needed to do that puzzle, right? I mean, there's no instructions here, so it's just the ID, but the ID is mapped to a hidden vector. And this 512 dimension vector here might already tell you the instructions for that puzzle inside here. And so we don't want to output the instructions. We just want to output, the final puzzle. So the final puzzle might be this white space here. Okay, yeah, Arvin, you want to say something?
No, I mean, I understand like it could hold many things, but even if it holds the ID, it makes sense to have something there. The output guy may not like it because it just wants something to compare to, but it makes sense to always have a topic underlined so that there is something constant going on. So I think maybe in the future somebody will try to incorporate this.
Yeah, maybe actually I think even if you put the puzzle embedding here, I think it should be fine. But the thing is the puzzle embedding and the sequence embedding maybe of a different substrate, I guess.
Yeah,
Yeah.
the reason I say this is because if it had been an autoregressive transformer where you're just doing COT tokens, then the token does not have any meaning. All it says is like puzzle ID colon, and then it is never going to change each time. But in this case, you don't know what's in there, and so you want to be able to have some special markers, on the margins, if you will.
Yeah, so I do think even if you put the puzzle embed in the final output, it shouldn't change much. Maybe it might be better. So they did an intentional decision to remove that. So I mean I understand why, because like they want to keep it pure. You see, like the puzzle embed is the puzzle embed, the sequence embed is the sequence embed. So if you want to predict the sequence, you take the sequence embed.
Yeah.
So yeah, I do think there's a reason for this. Of course, we can do some ablation to see whether we put the puzzle embed here, whether it works. It's a very simple change in the code. You just put instead of only the puzzle embed onwards, you take the entire length here and do an MLP, and then the output. It's just a one-line change in code. Yeah, someone can try it out and see whether it works.
Yeah, but it'll only help if that information loops back each time, but you only get a loss value outside the output. There's nothing else which is coming back in. So right now it doesn't make a difference. Yeah.
I mean, it depends on if your loss function goes through the puzzle embed, then your puzzle embed can carry the gradient back. But in this case, your gradients can all be carried back by the first few layers. Yeah. I mean, sorry, not first few layers. This white part. Yeah. So I just want to share with you something very, very interesting that I've discovered while reading the code, is that this puzzle embed here, this puzzle embed is used for the Q-learning. It's very weird. It's not mentioned anywhere in the paper. In fact, the paper says they use the entire head for Q-learning. So this is a discrepancy between paper and the code. They said this thing, I look through the code, I verified it. This thing is used to do Q-learning. So how this is done with Q-learning, let me just draw out for you. So this is mapped to a 2-cell output grid. And then this 2-cell output grid is either stop or continue. Q stop and Q continue. So basically, if let's say Q stop is greater than Q continue, then I stop. If not, if it continue is greater, then I continue. So it's like a 2-value thing based on the value. It's like your judgment, should I think some more? Should I continue thinking some more? This is based only on the puzzle embed. So I think in this architecture, they wanted to separate the complexity of the problem, maybe based on just this puzzle embed, which maybe tells us the instructions. Like the more instructions needed, the more you think. It's like a dynamic thinking based on your puzzle instructions. So this is something quite curious to me, because I think you should use the entire vector rather than just the puzzle embed.
Can I add to that, John? So I have a perspective on that.
Okay.
So
Yeah.
when you're doing training on the model, you are going to run a batch of experiments. So there is a bunch of problems being solved concurrently, right? So each of them have their own puzzle embeddings. So, and every single puzzle needs to have its own Q learning module, which is to say, for this particular puzzle, should I halt or continue? And each of those puzzles may be running for varying amounts of time, right? Some of it might be easy puzzles, you're done, and then the H module will come and say, oh, the L is free, so here's the new guidance, like let's start over. So I think that's where the puzzle embed really helps while you're doing training in batches.
Yeah, so that you can tell, okay, this puzzle is simple, stop early.
This is done, this is,
Yeah.
yeah. So the Q learning actually gets to see for every single item, every single task, so it knows whether this is a simple one, and it actually can learn. Yeah. And and you don't mix them up. Yeah.
Yeah, possible. So just want to highlight the Q learning, which is like the dynamic thinking flow, is based on the complexity of the puzzle, like based on the puzzle embed. So this is something that is not really well stated in the paper, because the paper said they use the entire output head. Okay, that's not true. I look at the code, it's not true, all right? So there's a discrepancy in the paper and the code, right? So if let's say the authors of the paper are viewing this, please update your paper or update the code, all right? Okay, so the thing that I want to highlight here is that the beauty of this architecture is that there's no instructions needed in language. The instruction is in the puzzle embed. And your L and your H module, by outputting exactly the same output, which is like 1 token puzzle embed and 30 by 30 token sequence embedding, at every layer, the hidden vector, the hidden dimension, the hidden vector is like the same number of tokens and the same number of embedding dimensions. You are able to do recursion with this. And you can do recursion at any level. Okay, I want to emphasize this point. The architecture allows recursion at any level, because the output token and dimension is the same. And also, I mean, the input is the same also. I mean, like input and output token dimension is the same. And that's really amazing, because that allows you to stack more layers. Like if let's say you want to do another one, like if you want to do an amendment to this architecture, you want to do, let's say, a H2 layer. you literally don't have to do any change to the block for this, because the block can just take in the same input and output. You can literally just have a new hidden layer here, and then you just take once every n or m time steps, you can take another hidden layer z0h2. You can literally just stack in the next layer like that. This module will be exactly the same as this H module and the L module. And the input and output is exactly the same dimension. You can mix and match, if you want, you can also put the L module back up here. It's up to you. It's very configurable because of the way the input and output are structured. This is much more versatile than a traditional next token prediction architecture, where, because you predict the next token, you may not be compatible because your token sequence the number of tokens might be different. It could still be compatible because transformer can take in any number of sequence as input. But the beauty of this is that by not doing next token prediction, it's much faster. Okay, much faster than autoregressive next token prediction. Much faster because you can output the entire thing at one go. Like normal transformer, you need to do one token and then you do again and do again. Here, by outputting everything as a hidden vector, which let me just draw the hidden vector again. By outputting everything as this, the puzzle embed and the sequence embed like that, by outputting everything as this, you essentially skip the auto regression step. This is actually very fast inference. I think it's like a massive speed up. I would say 10 times or 100 times. It depends on how many tokens you output, because this is linear time output. Like, well, for autoregressive, it's based on the number of tokens. Here, the output is all at once. It's much faster. It's like, if let's say you were to type in 100 words per minute, right? Now, with this HRM architecture, you can output the entire 100 words in the same time as your single word, all right? Or single token, because you don't have to do this autoregression at all. That might be why they omitted the autoregression. I think they might be looking at a potential speed up to transformer architectures by removing the autoregressive part. And that to me is impressive, because not every task you need a dynamic output. Not every task. Some tasks you are happy with a static output, like traditional neural networks to classify dogs and cats. You don't need to say, hey, this animal looks like it has whiskers and so it's a cat. You don't need that. You just need cat. Like some tasks you just need the classification. This really just goes straight to that. You have output which is like the classification, right? So just take a moment to appreciate how beautiful this architecture is, because by having the input and output being the same dimension, they can do recursive kind of thinking. In fact, this is also the same idea behind transformer blocks, because the transformer blocks also take in the same input vector and output the same vector. So really, this allows the transformers to stack many layers as well. But with this HRM, you are using the same idea, but you are able to do it over multiple hierarchies. So this is the same as with hierarchy is HRM. Yeah. So I think this is quite impressive, because this is something that allows you to stack, and you can stack in whatever way you want, right? And the output, because of the way you output all at once, you have very little latency. Okay, so one last thing here before I move on to the next slide is that the other thing that is beautiful about this architecture is the way they train the gradients, right? So the only gradients that they have is the embed layer, the L module, H module, and the final output head. And when you do a forward pass, you go through all of this. You go through everything here. But once you do the backward pass, you only go through like the last hidden layer for each of them. So like you go through the head, the H module, the L module, and the embed module. So they have some proof in the paper that says that this gradient is very is approximate to all the rest of the gradients. I think this is a good thing, because if you go through too much of the other modules, you might get gradient vanishing and gradient exploding problems. So just to highlight this. Okay, code. This is essentially the code. So here, every HRM block, we have the number of time steps where number of times you update your high-level module. So sorry, T is the number of T is every T time steps you update your high-level module, and then N is the number of times you use your high-level module. So N and T. So this doesn't have any adaptive thinking yet. This is just using the normal, let me just highlight for you. This N is the number of iterations of thinking, which includes the high and low, and the T is number of time steps before invoking high-level thinking. Right, so N here. So essentially, we just don't do any gradients at all, okay, for the first few updates. But every T time steps, I update my high-level module with the high and low input, and every time step, I update the low-level layer with the low, high, and X. X is the input layer. And then at the end of it, I predict my low level for the last time. I predict my high level for my last time, and I map it back to an output head to get me my output grid entirely. So the stuff in yellow here are the stuff where gradient flows through, because the rest doesn't have gradients at all. So this is quite cool, because this means that you only have gradient computations at very few points of the model. And as what I said last week, this avoids the problems of traditional recurrent neural networks, where because you need to update the gradient at every time step, you kind of run into the problem of gradient vanishing and gradient exploding problems, where your gradient becomes very hard to use to train because it's either too big or too small. All right. So this is cool. And so there's also another thing called deep supervision. And in deep supervision is basically for every XY pair in train data loader. And XY pair is basically like X is my input grid and Y is my output grid. Right? And all these are flattened. Okay, flattened because the transformer only can accept a 1D sequence of tokens. So we do this thing called deep supervision, where at every step in this deep supervision, what I do is I basically run through my entire thinking process. So you can think of this HRM here as one process for thinking. Okay, so like the process involves the number of iterations of high-level thinking and low-level thinking. So this entire thing is one HRM module. This is a meta loop over the HRM module. Okay, because it tells you how many times you want to use this HRM architecture for the same problem. But there's a difference here. The difference is this. The difference is that we have this Z. What is Z? Z is like your cumulative learnings so far. Right? Okay, why? Because initially when we start off, Z is a random init. All right. But once we keep doing this step, your Z is updated every time. So you see, your Z is essentially your high and low level. This is my Z, high and low level latent spaces, the hidden vectors here. Okay. And this Z here tells you what you have learned in your high level thinking and what you have learned in your low level thinking. It tells you what happened in the previous thinking steps and like what's the carryover. These are the carryover that can be used so that you don't start again from scratch. Okay, you have a vector that you use to condition your learning. And this vector here is like, if you were doing chain of thought, you'll be like, oh, I've executed action 1 and the result is this. Executed action 2 and the result is this. So that entire series of text, you can view it as your Z. And your Z has two layers. One is the low level hidden thinking, hidden vector, and the high level hidden vector. Okay, one cool thing is that based on your starting point, you can get different results. Okay, exactly the same architecture, exactly the same weights and biases, different starting vector. Because your starting vector is sort of like you use it because when they do this L and high module, low and high module, they actually use the hidden vector and add it to the inputs. Like so there's a kind of like this depends also on the hidden vector as much as it does on the input sequence. Yeah, so this actually has quite a high weightage in terms of processing. So when you start off with H and L that is the ZH and ZL that is something more informative, there's a higher chance you will get your answer because that has equal weightage to your input sequence. Right. So what we do is we basically do a comparison of whether each cell outputs correctly. And then this gradient gets fed back to the loss. Get fed back to the model to update the weights and biases. But one very important thing is that we detach our Z at every step that we do deep supervision. Okay. Can anyone want to guess, like, why is this necessary? Why do we want to form new gradients at every step of this supervision? Why not have the Z carry over to your previous thinking time steps all the way to the beginning? Like, do you have any intuition why we want to detach the Z at every step?
Initially, it might be that the Z would probably build up on the gradient over time, and it might accumulate with issues. You might get like you said earlier, like the vanishing or exploding gradient. Probably the exploding gradient, just because the Z is not being detached over time, and it's just going to keep building up and accumulating on the previous time steps until your gradient just goes all over the place. That initial analysis.
Yes. So this is my understanding. We detached Z gradients from earlier thinking steps, from earlier steps, because we do not want to learn twice. Okay, because like initially you already learn at time step 1 for Z1 to Z of for Z0 to Z1. Then like for time step 2 for Z1 to Z2. Like Z2. Like you don't really want to at time step 2 learn Z0, Z1, Z2 again. Because you are like relearning this again. Like, and this can lead to exploding vanishing gradients. But this also leads to an imbalanced kind of learning. Because we keep learning the first time step again and again and again and again. This is actually one of the least informative things to learn. Because Z0 to Z1 might be still very fuzzy. The hidden state might not be very well refined yet. Like, you don't really need to keep learning this. Yeah, so by detaching your gradients, you only learn what you need to for each time step. And it's more focused learning. Okay, so an analogy I want to give is like you are training a kid, all right? Let's say you are training your kid for doing something wrong, right? So like at year 1, your kid, climbs the sofa. So you punish the kid, right? So that's year 1. At year 2, your kid climbs the table. So you need to tell. Okay, so if you have a kid or a dog, like when you have someone that does something wrong, all right, at year 2, do you go to tell the kid, hey, you climbed the table, actually climbing the sofa is wrong also, like that's like doing a double teaching, right? Like, okay, maybe in this case you might say that yes, it's relevant, but what if year 3 is like this? Year 3, your kid spills milk on the table. Tell kid to be more careful handling milk. All right. So handling glasses. Yeah, so like if you were to think of it this way, in year 1, year 2, and year 3, like imagine at year 3 when I teach my kid, I tell my kid also, hey, you spilled your milk on the table. Don't climb the sofa. Don't climb the table. Be more careful handling glasses. That does it make sense? Because like we have already passed that year already. The year 1, year 2 are passed already. Yeah, but Arvin, you want to say something?
Yeah, this is a perfect recipe to fight the RNN vanishing gradient problem. And if the auditor is trying to look at this whole thing, you don't want to go through every single problem. So we're going to discard everything. Only going to look at the last thing that we have and say, we're going to punish you only for that. And since that state is going to be the initial step for the next M loop, anyway, that's going to be the main thing in mind for the model. So I think they get away with the all of maintaining all of that past mess by just focusing on the last problem, right? Which you might think that if a problem takes a very long time, let's say 500 steps to solve a problem, and somewhere in step 2 it went wrong, and as a result everything is thing. But even when you but that signal will still be there, right? It's a vector, so it's going to be there, and the next time you come around, that's going to really blow up and in importance, and it's going to find out. So I think this is great, that you can get away with this one step uh, approximation is a fantastic idea.
Yeah, and you avoid learning the same thing twice. Yeah, I think this is really cool. So if there's anything you want to learn about the HRM paper, is that gradients are important. They did very nuanced handling of the gradients, and I think this is why, in the earlier example they stack their architecture to great number of depths and does not really suffer from loss of performance, whereas the transformer and recurrent transformer does. This is one reason. Their gradients are handled better. They don't propagate gradients backwards for everything. They truncate it. They only do very focused learning. And this is something that we need to learn from. Okay. So what are the trainable networks in HRM? Over here, this math part, I'm going to just jump through like quicker because I don't really believe in the math. I believe more in the insights, okay, which I've covered already. So we have an input layer with weights and parameters in this theta, high-level module and low-level module, which if I said earlier, this actually is not just one set of weights and biases. This is actually a transformer module. High and low are transformer modules with stacked transformer layers. Each layer has self-attention. They also have a regularization, which is like the normalization. And what do you call that? Self-attention, regularization, and feed-forward layer. Yeah, so this is essentially what we have, all the parameters we need to train for low and high. And then we have an output layer here. So the input layer and output layers are essentially, like input layer is basically a dictionary mapping from token to vector space. Okay, but you can learn the dictionary mapping. It's the same as a traditional transformer. The output layer is an MLP, where you map from hidden space to output space. And you do this all at once. Okay, you don't do this one token at a time, you do this all at once. Right. So all these are the stuff that we need to train. We start off with I believe they use a truncated normal initialization for ZL and ZH. Basically just a random initialization. Yeah, just treat it as random initialization. Easier that way. Okay, low and high. And then you learn the Z low and Z high by doing the thinking steps, and you update the Z low and Z high every step that you do. Right? So earlier on, I showed you this vector where you have a puzzle dimension and the sequence dimension. This is exactly Z low and Z high. Z low and Z high will be trained to, to output this. So basically they output their input. What a great recursive architecture, right? You can just keep looping and looping and looping again and refine this vector here. Yeah, this is really cool. All right. Questions before we move on? Okay, all good. Right, so as what I said earlier, you need to do the low and high level and your input to get a new low level state for low level module. And a high level module, you get the high, low, and you get the high level module, except that you don't do this all the time. You do this every t time steps, which in math speak is saying I is congruent to 0 mod t. But basically it's just saying that every t time steps. Math likes to make things complicated. Actually, this is every t time steps. All right. Then otherwise you just take the same hidden vector. All right, as mentioned earlier, this helps to reduce the number of gradient updates. And also this helps to increase training stability as well. In reinforcement learning, this has been done quite often as well. You have two networks. one network keeps updating, and then after that, when this update is done, after a certain time step, you update the new network with the learn network here. So like a lot of the teacher-student models, they do that. The teacher only gets updated once in a while. And that's like what is done in AlphaGo and AlphaZero. Yeah. So this idea has been used quite often. There's also like other ways, like you have Q learning with two Q values. That's the same idea. Yeah. Arvin, yeah, you want to say something?
Though the ZH depends on ZL, not L I minus 1, because I think that was a typo and the author said they'll fix it. Somebody
Oh, no,
opened
no, no. ZH depends on ZH, I minus 1. I minus 1 is the time step of ZH. So what this means, that's why I say math is confusing. Let's go back to the diagram here. What this means is that your Z, oops, sorry. Your Z at this time here, or your H depends on the Z at this time here, which is depends on this. Basically the same. So like this ZH, after T time steps, then
Yeah,
it,
but I would have updated. So you're already at I, right, for that important step, not the one before. So that was the thing. And the somebody opened a Git issue and the author said they'll fix the typo in the paper, the next version.
oh, is it? No, but based on this diagram, if we just look at this diagram here, and I look at the code also, they literally don't update the high level module at all. High level hidden vector at all until you invoke the H module.
Correct, correct.
Yeah, so I mean, in terms of the code that we have earlier, in terms of that equation earlier, is correct because this ZH at time step I is the same as this ZH at time step I minus 1. I mean, you literally did not change the module, did not change the hidden vector at all, right? It's the same vector.
Yeah, for 1 to T, then it's the same. Yes.
Yeah, so if you look back at the equation just now, that's exactly what we are showing here. We are showing that the hidden vector for H is not updated if we have not reached the T time steps.
Correct. But
Yeah.
it depends on the current L, right?
Yes, when you update it, it depends on the L at that. Okay, so it depends. This you are saying the
On the
typos here,
previous
right?
L.
The typo,
Yeah, yeah.
this one should be at time step I.
I, exactly.
Yeah. So yes, there's a small typo here. So I think that's the one that you're referring to. And I agree because in your low at the time step I, it's also the same time as you update the high. So let's go back to that diagram again. So as you can see, the paper is not exactly very robust, all right? We have to bear in mind there's some errors, especially code errors, because what is reflected in the code may not be what is reflected in the paper, as I discovered myself. Okay, I actually spent a few hours, actually 2 days, looking at the code to understand it, and I realized discrepancies. So yeah, that's why I highlighted those in the earlier parts. So you look at this, right? This is time step I, and this is time step I as well. So yes, the timestep I low-level module, and this gets fed into the H module at timestep I. So yes, indeed, there's a typo there. Right, thanks for bringing that up. Yeah, thanks for bringing that up. So here it should be I. Okay, so after that, we do a prediction where we just feed in the output layer. We feed in the hidden state at the final computation, NT, timestep I, NT, and then we feed into the output layer using like a MLP, multi-layer perceptron. Just to let you know, there's also the meta thinking here, where meta step, where you do the whole thing again, but start off with the Z from previous step. So this is the deep supervision. So don't think that this is the end. All right, this is just one step in the deep supervision because you can still repeat the whole process up to you as many times as you want. All right. So I think that should be in the next slide. Deep supervision. All right. So we thought that was meta. Now this is meta. Like this is beyond high and low. You repeat the high and low again. So this is again based on the brain. But let me just give you the brief breakdown of deep supervision. All right. You have a hidden state from your previous time steps, and this hidden state is the ZL and ZH of M-1 of segment M-1. So earlier, Arvin was saying about segments. This is the segment. So this is like inception, like you already have a HRM module and then you incept it to go even deeper. Yeah. Okay, so this HRM here is low and high, and then you invoke the entire HRM again to get the output state as well as the new hidden state. So we can compute the loss for each segment, and then we can, based on this hidden state, we can feed to the next round of HRM again. And earlier we saw the the hidden timesteps, the timesteps, how the model visualizes. That is actually this thing here. At every segment, we can take the output here and we can visualize it to see how close we are to the output grid. And this is very important because the loss is based on the cross entropy loss in the token logits based on the output grid as well as the model answer y. So at every single step in deep supervision, you have a reliable gradient signal that is very, very objective, because this ground truth is always there all the time. So what you are learning is you are learning to make every intermediate prediction closer to the ground truth. And so, earlier on we saw let me go back to that picture because I think we viewed things better in pictures. Earlier on we saw that as we go through these time steps here, we get better and better predictions, all right? And this is very, very key because this means that for any start state to any goal, the goal state is fixed. We can literally not just do a prediction of like this to this. We can also do the start state to be here, which in this case is you take over your Z carry forward. Your input doesn't change, okay? It's just the Z. And then you can also predict here. And then you can also predict here and so on. So literally, you can shift your start state to any intermediate state and learn from it. This is very, very important because then you can learn near-term relationships to far-term relationships. So near-term relationships are those that are nearer the final goal, and the far-term relationships are towards the start. So literally you can learn problem solving from start to end. And that is very, very cool. In fact, if you have multiple goal states, you can also learn multiple goal predictions. All right. So this is something that I covered in my paper, Learning Fast and Slow. I think I covered this last week, where you can have, given a sequence of trajectory, you can learn from any start state and any end state. I think that would be the ideal because you can get so much more learning compared to a typical reinforcement learning thing where you only start from the start grid and you learn whether you succeed or fail. Okay, that's very, very sparse learning. That's not good. Here we learn whether every cell is predicted correctly at every single step of my deep supervision. And that is very powerful. That's very powerful. In fact, this is probably the reason why this paper could do so well. The reward signal propagation is very good. The objective signal is very good. You learn not just from the start to end, you learn at every intermediate step, and you carry over your Z, which is your intermediate thoughts, every single step. So you don't start from scratch. At every time step, you learn from the teachings of the past. And I would like to say you only get better, unless your thinking is wrong. But because you have a supervisory signal at every time step, it is very unlikely your thoughts will be wrong because you have the ground truth at every time step. Okay, so this is very cool because you don't need human labels anymore for chain of thought. All you need to do is have a ground truth at the end. You can use your ground truth to learn every single intermediate time step. Wow. This is if the earlier thing about recursion of the vectors is not enough, this is the highlight of the paper. Yes, Derek, maybe ask Derek first. Derek, you want to go first?
So this part of the training process, this wouldn't happen to be unique to the architecture, would it? Like, is this extrapolable to like multiple settings, or do you still? Because I don't think there's a reason to need the current architecture. This time step ground truth referencing can be done with a much more run-of-the-mill model, even probably just make an augment to like an RL system, a couple augmentations. I don't see why you can't implement this in a more typical model system, training pipeline system.
You can. Just not a next token prediction transformer because unless you have control of the model, you can't get the hidden steps. But you like, let's say the OpenAI open source models, you can get your hidden vectors from that model. Then you can run this algorithm over it. Like, in fact, you may not even need to use transformer models. Any RNN, neural network, as long as you have access to the hidden state, you can do this. So yes,
This probably would be amazing with Gaussian architectures because the time space is very reminiscent of like the what are the fusion modules? Sorry,
yes,
the fusion models and their Gaussian process. This would probably work amazing with their time step algorithm.
indeed, indeed. I'm very excited for applications of this kind of like learning from every intermediate time step. I think that is very generic, can apply to any model as long as you can extract out the hidden state or in fact, it may not even need be the hidden state. You can also do it some other way, as long as you can have a way to get the output from your model, and then you compare with the output for your final model. Like you can, as long as you can compare outputs, you can do it in any model.
Gotcha. Okay.
Yeah.
Thank you.
Arvin, yeah, your turn now.
Yeah, I mean, you have to stop me. I'll get. I'm so excited that I'll get carried away.
Please
Uh,
get carried away. Yeah.
so first of all, yes, it's a general purpose idea. Completely agree with what Derek said, and it's a plug and play thing, and it's probably the highlight of the paper. So for me, it's like you're not just thinking fast and slow. You're figuring out when to think fast, when to think slow, how long to take, and you're doing that. And this might be the first time I'm thinking like beyond the loss function, there is somebody on the inside your mind, somebody which is telling you and tracking at a meta level how are we doing, right? Like earlier, it's just the external signal. The world is telling you, do better, do better, and then you go adjust the knobs. But now you're also internally tracking, which is fantastic. So that's where my excitement comes from. Yeah.
That's cool. That's cool. Yeah, I really like this paper. I really like this paper, except for the fact that some parts of the paper are different from the code. But the gist of the paper is awesome. All right, let's move on to
Hello, sorry, I have
yes,
question.
sorry, yes, go ahead.
So, can you clarify what do you mean by there is a ground truth at every intermediate state?
Okay, yes. So at every step of this deep supervision, the model outputs the final output. And so you have the ground truth output Y, which is like because if you have a training set of X and Y, where X is your input grid and Y is your output grid, you already have in your training set, you already have the output grid, which you can use to, check
Can you
whether,
use the example in the previous slide?
yes, yes, can. So if we use this as, let's say this is the ground truth, and your Y hat is your predicted. At every time step, you have a different Y hat. So this is Y hat for time step 2, this is Y hat for time step 3. You can actually do your cross entropy loss for every single cell of this grid, compare this grid to this grid, and get a loss function for time step 2. You can also get a loss function for time step 3 as well by comparing this grid to this grid. So
Okay, okay, I see. So the Y, the ground truth is still the very last terminal state. Uh, I see, but I guess it makes sense for the maze problem, but I don't know, like in a more general setting, where let's say we are want to work on the math problem, then every time are you going to compare your intermediate working with just the final answer?
yeah, so if you want to apply this for math, what we need to do is we need to compare. Like you take your thinking after like 2 time steps, you output a final answer and compare to final answer. But for math, it's a bit difficult because you might be getting a wrong answer, but you're only missing one step. Yeah, it's a bit hard to,
And
objectively state,
it's not just the
incorrect.
wrong answer, it's also sometimes the intermediate state
Mm,
has no obvious like link to the final result. Like this, if there's some missing step, you sometimes you cannot see the link, but actually that's the correct working. So I don't see, yeah, it's like I think it makes solving a maze puzzle it makes sense, but in a more general setting, when you have some intermediate state working towards your final goal state,
mm.
it may not be very it not be very straightforward to derive a loss term you can optimize on.
Indeed. So for this kind of puzzles, you might need to do a graph-based loss. Like for example, this is your start goal and this is your end goal. It may not be a 2D grid anymore because like your graph could expand like infinitely, but maybe only one branch leads to the angle. But let's say if more than one branch leads to the angle, then it's not a trivial problem anymore, because you could be at this branch here, and then you might think that, oh, it's actually wrong, but because you think that your angle is here, but actually if you proceed down some more, your angle is here. So for cases like this is not covered in the paper, by the way, because you look at their maze, there's only one route. What if there's more than one route in the maze? Then there'll be
So is it problem specific? Is
it is
the
problem
loss?
specific, yes.
So they
Here,
need to design a loss for each type of problem they need to solve, right?
yeah, here they simplified this by choosing only domains where the answer is unique. So like Sudoku, the answer is unique. As for the puzzles they choose, I mean, some puzzles may be non-unique. ARC challenge, the puzzle is answer is unique. The
Yeah, I mean,
maze
I
that
mean,
you
like the
mentioned,
loss for Sudoku is different from ARC, right? The how
oh, it's
it
the
works.
same. It's the same,
It's the
because you
same.
just treat each cell as just a cell with a certain number of output tokens, output vocab size. Like here, your vocab size is 9 because you can choose from 1 to 9.
I see. I see.
And here the maze is either start, go, empty cell, wall cell, or your path. So there's 5 tokens here. And then
So for maze, it's not like I'm measuring the distance from my current.
no, it's not. It's
Okay,
just
I see.
basically
I see.
outputting this blue color.
I see. I see. I see. Oh,
So
that sounds more general. Yeah.
so everything, as long as you can map it back to like a grid. In fact, it may not even be a grid. As long as you can map it back to, you just need to map the problem. Let me just draw here. You just need to map the problem to a series of tokens with fixed token value, or with fixed classification, maybe, or vocab. I mean, they call it vocab here. So as long as you can have your problem mapped to a series of tokens, and each token takes on certain values at the end, you can use this algorithm to train it.
So do you think this way of design loss can generalize to the problem I just described, like a math problem? Do you think it will work?
No, because math problems, as I say in this graph here, typically you only want one path from start to end. If you have multiple paths from start to end, let me just write here. Okay, if you have multiple paths from start to end, you can reinforce wrongly. Because what happens is that you might say that, hey, the only good path is this path. And everyone that, let me just draw here, the only good path is this path, and everyone must follow this path. But you have forgotten that actually here can reach also. So this is the typical example of traditional education. All right? Because every time you only have like one model answer. But what if, what if you can succeed in more than one way? All right? So that is very hard for an objective scoring to be done, as what has been proven in traditional education. Like we always try to encourage people to be creative, but our marking rubrics are still fixed and very rigid. Yeah, so this is a hard problem to solve. We haven't solved it in education yet. That's why you see it's much easier to mark math and science papers than it is to mark humanitarian and social science. Because sometimes your view might be correct. You might say that
Oh,
communism is
okay.
great. Yeah, but
I see.
let me finish it. You might say that like communism is great. They give examples, but then if let's say the bias of the teacher is like, hey, communism has failed before. We should be capitalistic. Like you might just shoot down the student wrongly because you don't agree based on your view of the world. But there could be a different way of viewing things. Another example is like the FedEx paper. Have you heard of the company called FedEx? We live to deliver, right? The essay was given like a D grade or something. The entire paper describing the FedEx system was like a failing grade, or very, very low grade. And then the student was so unhappy, he said that I'm just going to implement it, and it became FedEx. So there are more than one way to succeed, but even traditional education has failed to grasp on how to reward multiple pathways. Same thing for academia. We have a lot of groupthink in academia. People publish the same kind of papers. Transformers very popular. Everyone use transformers. What if another architecture is better? What if we haven't explored this pathway that can lead to the end goal? So I would say that we haven't solved this, and I don't think we will ever solve it because there's just too many things to compute.
So, and it also has to do with the observability. So all the class of problems that they are attempting to solve have full observability. You get to see the entire board, and you can compare. And the loss can say, "Hey, this part looks completely wrong," because it's just trying to compare with the final state. And then it gives the guidance to the H module. H is saying, "Hey, L module, just go look at that part." But now with problems of partial observability, you don't even see the intermediate states. What are you even comparing against? So that's where the graph might be a way. So I think for the reasoning is such a hard thing. Like for one class of problems, definitely this might be good, but beyond that, I think we will have to think through math. As in, if you work out every single step and you make a very clear mistake, maybe the loss can point that out somehow. But otherwise, we are not even seeing all of the steps, right, in many of the problems.
Yes. Okay, so that was a great question, by the way. I think this helps us to see how generalizable the architecture is. And we still haven't solved the case with many, many different paths to the end goal, unless you can map it to an abstraction space whereby the end goal is just one cell. Right? So mapping to abstraction space is very important. So maybe you might not be able to solve this in the output space. You might be able to solve in latent space. And that's where you can look at the series of wonderful models by Mehta, Yan LeCun, JEPA, Joint Embedding Predictive Architecture, where the loss function is not in the output space, but in the embedding space. That might be the trick to solve problems that have more than one angle. All right.
Absolutely. Yeah. Thank you.
All right, so let's, in the interest of time, I'm going to take about 15 more minutes. So I understand that it's already more than the 1.5 hours time slot, but it's really such a great discussion. All right, let's not waste it. All right, I'm just going to end off in the next 5 to 10 minutes, and then we have a discussion for 5 minutes. So just want to say that they tried to do one step ahead. All right, they tried to say that, hey, earlier in deep supervision, we only have we have a fixed number of segments. What fixed number of times we repeat the deep supervision for? What if we learn this dynamically? What if we learn this dynamically? They're trying to outsmart themselves. They're saying that, hey, maybe having fixed number of thinking steps is not good. Shall we let the model think for itself how long to think? Wow. But unfortunately, I don't think they did it very well here. All right. So but the idea is remarkable. All right. So we have a Q values to say that, hey, whether to halt or continue. So we use the final state of the Q of the H module. Sorry, that's not the final state of H module. That's the MLP step, right? We use the final state of the H module, which is this here, and then we basically run it through a multi-layer perceptron to say that if this is your final state of the H, this is your hidden vector from the H, ZH. We basically run it through an MLP, and then the MLP has only two outputs. This output here is basically halt or continue. Okay, and as I said earlier, it's not the entire ZH they use. They only use this part here. That is the black color part, which is the puzzle embedding. This is not reflected anywhere in the paper, so I guess they should put this in the paper. Yep. So there's halt and continue over here. That basically tells you, like, if let's say halt is like 2.3 and continue is maybe like 1.5, 1.4. If halt is greater than continue, then what I should do is I should halt. All right. So you just see which one is bigger. All right. So you might ask me, why don't we just output one value, 0 or 1, right? Continue or not. But if output 0 and 1, the training might be a bit harder because you cannot learn this like sort of intermediate values. Here, at least you can learn the intermediate values. It's how do I put it? It's more variables to play around with than just learning a continue or halt binary signal. Okay, this is just a training trick. All right. Right. So how do we learn the values of halt? Learning values of halt basically is just saying that halt is basically saying we see how good current prediction is. So if the current prediction is very good, then yes, you can halt. Okay, over here you can see that this is the prediction correctness. So what this means is that it will likely not be a 2.3 and 1.4 here. It might be scaled down to 0 to 1. Okay, I say might be because I kind of forgotten how they did in the code already. But if they're comparing with how good the current prediction is, it should be scaled down. There you have a better comparison. All right. So next we have the probability of continue to be hot if we have reached the max time steps we have allocated for. Or we take the max of hot and continue, which means that what this is saying that is actually it's a very complicated way to say something that, like, is the best value of the next time step. Okay. So basically we are saying that, if you want to continue, then yes, I'll just take the reward as the reward for the final time step that you stop. All right. So this basically encourages the model to stop early. All right. Whenever the model sees that this thing is very close to 1, if this is very, very close to 1, which means that it's entirely correct, we should stop. Okay, because if not, it will keep going on. Of course, it doesn't look like there's a penalty if you keep continuing until the final time step. Because like if you keep continuing until the final time step, your max over here looks like it will still be the same, right? Like if let's say unless of course you overthink things and then your final correctness becomes worse, then you should stop here. But if your correction, if your what do you call that, your accuracy increases all the time like that, there's no reason to stop. So then essentially you will just stop only at the end of your n max. Okay, so over here, I think can't remember already because I didn't pay too much attention to this Q learning because I thought it wasn't very good. Right. The idea is that maybe they should put a kind of a decay factor whereby every time step, you do an alpha here. So this decay factor will basically be a form that is smaller than 1 and greater than 0. And this basically helps to make the model like prioritize stopping early because the reward gets lower and lower as you continue. Okay, I don't think they did this in the paper. Not sure whether they did this in the code. I just want to highlight that this loss is fed in, okay, to the normal model loss. And they have a second loss term that says like how good is, my G. That when you basically how much is the G the same as Q? Like G is basically the okay, so G is the target for the actions and Q is your intermediate predictions for your Q learning target. So they basically try to say that I want to make my Q be as close to G as possible. And G eventually will lead to here, to your prediction correctness. So what this is saying is that I'm trying to make my intermediate Q values be as close to the ground truth G, which in this case is the prediction correctness. Yeah, so this is essentially what they're doing. Okay, I think whatever I said here is just a primer as to what you can do to do the kind of like when to stop and when not to stop. Because if you look at the TLDRs, use the two scalar reward values to see whether to stop thinking or to continue thinking. Because if you look at this here, they call it adaptive computational time. Okay, if we have a fixed M, okay, which means a fixed kind of deep supervisory step, you can see that it continues to scale up to like 8 if the fixed M is 8. But the ACT is about only 1 step. But you look at the ACT performance, for about 1 step, the performance is very, very like at first it's not very good with M fixed 2, but with M fixed 8, ACT apparently can reach the same as a fixed M, right? And they only use like about 1 compute step, which is kind of impressive. Like how they managed to use only 1 step and achieve the same performance as 8. I don't know. I mean, they only use 1 step. Essentially, the forward pass is the same, right? Okay, so over here, in inference time scaling, you can see that here, when you have your mx being 2 and your mx being 8, your inference here is very, very close to 100. So you can see over here, models trained with a specific mx can generalize to higher computational limits during inference. So what this means is that like where's my ACT in C, right? Mmax, if you train with 8 and you you do inference time scaling, kind of looks like it can do much better than ACT. So this is the ACT performance here. Like, I'm not even sure how this graph is computed, because you see this is fixed M of 8, right? And this is Mx of 8, but this is much higher than this graph. So why? So I honestly, when I look at this graph, you know what this tells me? This graph tells me that ACT is not good. Okay, because if we just train with a fixed M, which means that I have my fixed upper limit, I just scale my upper limit to the highest possible. It doesn't look like it's dipping down. It doesn't look like the performance goes down like that. No, it doesn't look like. It looks like the more you train, the better the performance. And like, why is there a need to do adaptive compute time? Like, you can tell me, I'm opening up to the floor here. You can tell me why ACT is good. I don't see any benefit other than, maybe reduce the number of compute.
Diminishing return.
There's no diminishing returns here. The graph is always going up.
No, by diminishing return, I mean you pay from 8 to 16 is double the cost, but the increasing is marginal.
Sorry, increasing the cost, but the what? Say,
You go from 8 is around 98, right? Or 90, I don't know, like below 100. But from 8 to 16 is, yes, it increased, but it's so minimal. So does it worth to pay another 2 times of the cost, inference cost, to just get that marginal amount of increase?
Yeah, you make sense. Yeah. So basically, if you can basically make the adaptive compute time such that it's able to do like only 1 step or 2 steps and perform much better than or about the same as your fixed M, the compute cost will justify it, yes. But what I would say would justify it if they had shown the next level. So I realized why it's different already, because this is 16 and this is not 8. So what will convince me fully is that if my fixed M dips down here, while my ACT continues to go up, which means that, overthinking is bad. I'm not even sure whether this thing here is the fix or the ACT. I suspect it's the ACT. So if they can show me that there's one time step here that your fixed compute is horrible while your ACT can still continue to go up, I will buy into ACT. I just don't really see it here. Yeah, so correct me if I'm wrong. Like I mean, that's why I say the paper is a bit hard to understand. I don't even know whether this is ACT or not. I guess this is ACT. Yeah. So
I think we'll have to do some studies with different size data sets and different kinds of problems to really grasp this deeply.
yeah,
Uh, I mean, with such a few parameters and just few examples, it's so good. Then what is bad? So you need different benchmarks. So we'll have to do some training to study this.
correct. So actually, if you look at the graph here, like, because this is not explained in the paper very well. If you look at the graph here, let's look at the point-to-point comparison. This is 92.5 for fixed M. This is 92.5. This is 97.5 or so. This looks like fixed M to me. This graph looks like fixed M. So um where's ACT? Where's ACT? I don't know. I don't know where's ACT. Like, if you ask me, ACT is not really very good. Like, so I wouldn't recommend using it unless I said earlier, you can show me that there's a point that ACT performs more than fixed M, but they haven't shown me that point. So
Do they have the same charts for the maze? Because
no,
Sudoku, I understand.
no,
Because
I think
there, I think it might be you might be able to see the curve go up a lot more. I
this is
mean,
the
that's
only
my
graph
hunch.
about ACT I found in the paper. Yeah. So
Understood.
if you look at this thing here, like, this whole thing is still pointing to how good your prediction accuracy is. I mean, if you think about it, like, this is already covered in the loss function here. This just tries to map another loss function of G to Q, and by having this loss function here, you might actually affect the loss of this, because you split your training pathway into both. So I think this unnecessary complication of the entire model, and I think it's a great idea that they try to do some adaptive thinking, but I think the adaptive thinking could be done in a threshold rather than this. Like you can literally just do this prediction at every time step, and then based on your training, because you have the puzzle embed, right? Based on your training puzzle embed, you can already. This is my take. Okay, my take. Just based off average steps needed to reach a threshold accuracy in your training tasks, and use that for tests. I mean, why do you need to train a Q-learning model for this? I'm saying this because I have a personal bias against Q-learning. I've done reinforcement learning for 4 years. Q-learning is the most inefficient way of learning. All right, it just takes too long to update, and by the time you update, you might be incorrect for the new context. So for me, explaining this slide was a pain because I experienced the horrors of training Q-learning again in my head when I explained this slide. So this is to me not a very good way of learning. All right, this Q-learning method is not a very good way of learning. It takes too long. Even you take the landmark DeepMind paper called Deep Q Network, they spend millions of time steps learning. Are you going to spend millions of time steps learning this Q? Again, this complexity is a bit lower, but the idea is that you're trying to approximate a value that is the loss function here. And then like if you look at the other terms here, it doesn't really make much sense to learn any of this. Like the G continue is what? Go to Q hot. What is Q hot? Q hot is going to be G hot. I mean, like essentially you are trying to learn when to stop based on a threshold, and that threshold is going to be kind of different for each problem. And you're trying to learn a Q model that predicts this based on every problem. And why not just use like there's this thing, some tasks doesn't need neural networks. Like you just use rule base to determine when to stop. What's so difficult about
Sorry,
that?
how do
Why
you
are we
use
using
it to determine?
Q network for this? Yeah.
How do you use rule-based?
Oh, just here. Based on your training step, you have a threshold accuracy. And once your threshold accuracy is reached, you take the average number of steps for your training task and use it for the test task. Because in your test task, you have no access to correctness because you don't know the ground truth, right? So you just based on your training.
Yeah, that might be more optimal. At least humans do that. I do that. So hey, this looks harder, maybe we should try some more. Or like, I know I'm gonna I think I'll stop here because this is sufficiently solved, right? So that's a approximate rule that you make up by averaging, so it makes sense. Yeah.
Yeah. So I don't know the results. My inner researcher radar is tingling when I saw this graph. Um, doesn't look convincing. All right. So some parts of the paper is great. I already expounded on how the recursion is good, how maybe you can output all at once. Maybe that's good also. But this graph just doesn't cut it. I mean, like I'm sorry to the authors. You haven't convinced me. That is good. All right, let's just, okay, I'm so sorry. I think I need another 10 to 15 minutes. I hope you are okay. Let's just go through this. This is what I realized after I look at this paper and I compared with similar architectures. There's this thing called GLOM and graph neural networks that look quite similar, but they haven't really did quite well. And they haven't really done quite well. Let's see why they have failed, all right? So GLOM. GLOM is by Geoffrey Hinton that says that, at every level of my hierarchy, I will have lower level conditions, higher level conditions, and same level conditions. Can you see that this looks kind of similar to HRM? Let's take out the top layer. Let's just take a look at here. The only difference between this and HRM is that at the top level, I don't have that many. I don't update this as many times as here. Maybe I update. So for HRM, you don't have many top level stuff. While for this GLOM is everything at all at once. So I suspect that GLOM might be a little unstable in training because you have too many gradient flows, right? So if anything you should learn is gradient management is key. Don't do feed forward steps unless they really matter. So the difference between HRM and GLOM from Geoffrey Hinton is that GLOM has too many connections. And I think this is something that we can learn from the HRM paper. Just have fewer connections, update less regularly at the top layer might be already enough, and it leads to more stable training. Yeah, of course, more stable training needs to be in asterisk because we don't know. Okay, unless someone can implement a GLOM-like architecture for HRM that updates every low-level step, update every high-level step, and we compare with the architecture that updates only once every t time steps, and we see the difference. Then we will know for sure whether there's this cause instability or not. But my gut feel tells me that too many gradient connections is not good. Right? So maybe that's why GLOM hasn't really produced a successful result yet. Comments, questions, anyone? I think this is a great slide to discuss because this GLOM was quite big when it first came out in 2021, but we haven't really heard much news from it ever since. Okay, I think all good. So next is graph neural networks. Graph neural networks basically is like a transformer, just that you have a graph instead of input tokens. And at every time step, you do this thing called accumulation of the gradients to every node. And then you have a certain message based on that, based on what you have accumulated. And then you do message passing to put the message back to either a node, to edge or something. There are many ways to do graph neural networks. But the idea is message passing, where you accumulate information across your neighbors and you pass the message to something, all right? So there are many mechanisms here. They try to use this to solve dynamic programming, which is naturally a recursive algorithm. And I just want to show you this paper by Datzik and Velikovic. They tried to use graph neural networks to try to do recursive things. And I think the best performance is like maybe about 39% average accuracy when it comes to approximating an algorithm. So why am I showing this slide? HRM is like approximating an algorithm in a neural network. Okay, why do I say that? Because like stuff like solving a Sudoku, you're approximating like the dancing links algorithm. Maze finding, you're approximating a breadth-first search. Let me just write this down. Sudoku is like dancing links, or I mean, you can also do depth-first search, but it's going to take quite some time to do it. Or like maze finding is approximating a breadth-first search or A-star search with heuristic. Arc challenge is approximating many different algorithms. Because like it could be like if else, it could be a for loop, it could be maze pathfinding, there's many different things. So how good are neural networks to approximate an algorithm? That's the key question, because essentially HRM is a neural network. It's a transformer, but a transformer is also a neural network. And there are some things that an algorithm would do very well, like pathfinding. And there are some problems that neural networks would do very well, like classification of dogs and cats. But if we use a neural network to solve maybe maze finding, I don't expect the neural network to be 100%. And indeed, if we just take a look at the maze, if you just take a look at the maze grid here, I'm gonna have to go all the way to the front again. If we just take a look at the maze hard and the Sudoku extreme, take a look at this. 55% for Sudoku extreme and 74.5% for maze hard. What does this mean? This means that algorithms are still better. Here is like, you're using a neural network to solve an algorithm problem, and we are saying that, hey, neural networks suck at it or are not good at it. But actually, we are just comparing half of the spectrum. I mean, we are not comparing everything. We are only comparing neural networks to neural networks. But there's a class of algorithms that can actually solve everything 100% of the time. And very reliable, very fast, even faster than neural networks. So the question we have to ask ourselves is that, are we using neural networks for the wrong things? Should we focus on approximating algorithms here? Or should we focus on doing things that algorithms can't, like more fuzzy logic kind of things? So here the paper's examples are all on very, very algorithmic tasks. And what I'm afraid is that, this might be nice to do, but it's not the kind of things that we are necessarily interested to solve, because there might be better ways to solve it, like using an algorithm. So I'm appreciative that, this might be able to solve problems that maybe you don't even know the algorithm for. Then yes, maybe that works. But as you can take a look from this graph neural network paper, like even graph neural networks are by nature recurrent. Trying to learn a recurrent algorithm like Dijkstra, Floyd-Warshall, it's already difficult. It's not even that great. Like, so that's a note of caution here, is that maybe this recurrent architecture might be trying to approximate an algorithm, but I don't think it will ever reliably replicate it. So yeah, only use HRM if your tasks cannot already be done by an algorithm. So let's put here, only use HRM if your tasks cannot already be done by an algo. Or another way of saying it is that, in agentic architectures, right? Only use agents if your LM pipeline cannot already do it. LM or rule-based pipeline. Okay, so a lot of times we see very cutting-edge research and we say, wow, it's state-of-the-art kind of thing. Yeah, but sometimes you might want to ask yourself, is this the best way of doing this? And so I put this slide here just to showcase, yes, we can have intermediate trainings of input to output, intermediate outputs to final output. But not everything you want to learn this way. Because if you don't have to learn it, then don't do it. Yeah, you can just use whatever that works already. Arvin,
Yeah, so I agree. One of the things I was thinking about is um if in the future you have tools, right, that are neural networks. So currently, all of the tool calling, function calling is all API calls which go to external functions, other programs. But I thought it was nice to have an HRM which is a neural tool, if you will. But again, the substrate, the LLM has to make the right decision. Should I send this to the a Python code writer which can actually write the Dijkstra's algorithm or A star, as opposed to go sending it to the HRM and trying to figure out the algorithm and reinvent it. Uh, yeah, I mean, I think it needs to be seen what how good the 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 router becomes down the line. Yeah.
mm. But that being said, I just want to put a note of caution here because I don't want to just go, wow, 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 HRM is great. I still think HRM is useful. It's highlighted to us how we can train our neural networks better, and how we can train intermediate steps better, and how we can implement the hierarchy better. So here are my thoughts before we go to the discussion. I think iterative thinking has its benefit, and it can help to solve the problem in small bits because you carry over the ZAG, right? You really learn what you learn in the start. And you can create like error correction also, like earlier on you might do something wrongly, at later steps you might solve it. This is great. This is great. Impressive that this is done with no logic at all for pathfinding and Sudoku solving, and it can still solve. This might be useful for algos we don't even know. Okay, so as I said, if algo can solve it, use it. But what if you don't have the algo? Then the HRM would be very, very useful until we find the algo for it. Right? Benchmark tasks are great, but they are only great tasks. Maybe if we could have some language tasks that can be used to provide instruction to HRM. Like for example, you could have like put ball X, put red color brick on top of green color brick. Then you can do like brick wall. Like this is your task, and then you can have a red dot green. Then this is your input, and then your output will be like green, and then like red, then slash n, then red dot something like that. Yeah, so you could. I mean, depends on how you want to maybe you want to represent your grid as a 4x4. So you have red dot green slash n dot. Yeah, then this one become like that. So red on top of green, so it'll be like that. Yeah, so you might be able to represent your task as a language task, and then your grid over here. So it's something like your puzzle embed. So instead of having a puzzle embed, can I replace puzzle embed with a language instruction, and then embed the language instruction as an embed? That might just be as simple as passing another transformer to map that input token into an embedding, and then use the embedding as your puzzle embed. Yeah. you can backpropagate all the way to the starting transformer. In fact, the transformer that maps to the embed, you might be able to just use a pre-trained transformer so that you don't incur like training costs for your language, or you can just train from scratch. Yeah, so it'll be interesting if we can use language to condition it, and if we can output language as well, so that we can have access to like how the model is thinking. But outputting language in intermediate steps might be difficult because you need like some form of a human input to train the intermediate token output. So, but if we can just have as a instruction output input the language as well, that would increase the generalizability of HRM, because you can use your human prompts to change the behavior of the model. Imagine you can change the algo use just by talking, just by using human language. You can say, I want to find the shortest path, then it will use Dijkstra, Floyd Warshall. You can say, I want to replace the with then stuff like this, that then you can make the model be more performant in across more different tasks. Yeah. So yeah, that's what I was saying. Also, like perhaps we can visualize language output also by doing forward pass with a latent state, and then you do autoregressive token prediction. But needs human output training samples. So this might be difficult because the idea of HRM is that we don't want to have so much human labels, so many human labels. So this might go against the spirit of it. Okay, so at least I think the language tasks, I'm interested to see whether this works, because this will mean that it's a more versatile architecture than just having everything as puzzle IDs and embedding it. So the next step is to see whether HRM can do planning, simulation engines, visual module interpreter, because right now HRM only takes in the input grid. Can I have HRM take in other things? So other than, now it's puzzle token and grid tokens. Can I take in like planning tokens, simulation output tokens? Because right now in human language, I can put everything: planner, memory, simulation, vision module. I can put everything in language. Okay, maybe vision module cannot. Vision module, maybe you have a visual tokens here. Yeah. You can, what if you can interpret all sorts of tokens and use that as your input? That would be more versatile. And that's what a transformer can do. Like a traditional state-of-the-art transformer can take in audio tokens, vision tokens, text tokens. That's like Gemini 2.5, the multimodal transformers can do all this. It can output multimodal tokens as well. So if HRM is truly going to be the architecture for everything, we need it to output and input those kind of multimodal tokens. I mean, I don't need it to take in human language. Yeah, I don't have to. But it needs to take in at least the latent space. And that's going to be a challenge to see whether it can scale up, because that means our input space will be a bit more versatile. It's not just a recurrent input loop anymore. The input loop can be everything at once. Like it can be all these tokens at once. And the output, I granted the output can still be, the output can still be puzzle tokens and grid tokens. But at least for the input, needs to be more versatile. All right, so this remains to be seen whether this can be done. Okay. Any comments, anything on this slide? Good. Okay, let's move on to my thoughts number 2. Again, the recurrent loop that we see the HRM do, the low and high loop, might be already done in traditional LLMs where they perform this thinking step by stacking multi-headed attention blocks. So, when you do attention module, this is your transformer block, right? Transformer block 1, go in here, you have a skip connection. Okay, like this. Transformer block 2. I mean, if you think of a transformer architecture like this, is this the same as your low level block? Go to a high level block. And then output. Okay, of course, in the HRM, you can have more than one low level block. So this is my HRM. And of course, your low level block also can take in the high level. Yeah. So So this is HRM, and this is your transformer. So the question is, if we stack enough layers, can we approximate the HRM? Okay, maybe. I think this is possible, but gradient flows are a problem. Okay, because as we saw in the scaling slide, transformer scaling it do that not as good as HRM. So I think a traditional transformer can definitely approximate the recurrent cycle. It's just that we need to stack so many layers. It's not that feasible. So there is still a justification for a recurrent transformer architecture that HRM is doing because the gradient flows better. All right, so that's one. Next, the subject of thinking is currently language, images, audio in terms of tokens, but it could also be made to grid tokens. So again, this is in terms of traditional LLM. Okay, not really traditional, multimodal LLM. Yeah, because and multimodal LLM can also take in grid tokens if you train the grid tokens. In fact, it can just be letters. Like when I did Arc Challenge, I just use A, B, C, D, E, for grid colors. And that worked pretty well already. Yeah, you don't use numbers for grid colors because 0, 1, 2, 3, sometimes the relation they say take 1 plus 2, output 3. They think it's an addition thing. So the kind of semantics is not very good for numbers, but if you use letters, it's quite good. So the thing is, traditional LLMs might be able to do what HRM is doing by basically mapping the grid tokens to language tokens. Or you could just train special grid tokens for it. I'm just thinking whether if you train the grid tokens and then you use the data augmentation pipeline that they have in HRM and use the multiple like inference pipeline where you run 1,000 different inferences with different mappings and then you do the inverse mapping. Just thinking whether LLMs that have this training pipeline, can they do better than HRM? So my guess is yes, because transformers have a lot more inbuilt knowledge inside. But HRM has the benefit of being small. So this is a question of, should we do small scale models, large scale models versus scale everything models versus small scale specialized models? Yep. So this is the thing. I think there's no clear answer to this. Yep. Okay. Yep. So the next is the last point is LMs are heavily reliant on training data. So if we, this is basically my point that I mentioned earlier. Right, so I think there's a lot to consider. HRM is a great architecture, but it has a lot to do before it can approximate what the LLMs can do. But the LLMs itself, with a few tweaks, can already do what HRM is doing. So this might be a not so good selling point for HRM. Like HRM is really too specialized to be general. But I do think we can use this HRM-like architecture to train our transformer models. I think that's possible. Then we can have a generic transformer input-output that uses a HRM-like thinking. So that is summarized in this slide here. So this is the traditional LLM that uses language. Okay, right now with multimodal, we can also have multimodal tokens. And this is HRM that uses basically you take in everything as language and output everything as language. This is the traditional text-based transformer. Multimodal transformer, you can output multimodal. For HRM, you only put in the input grid. And of course, you also put in like the puzzle ID. And then the output is latent space. And then in the end, you output the entire grid, fixed length. But what if we can do a hybrid whereby, your input would be multimodal input. And then you pass through all these tokens in the same latent space. And then you go through your intermediate thoughts in both language and latent space. And also allow for two use. So the two use can either be a latent space or language. So essentially, in a traditional transformer architecture, we only have language output. But what if we can also output the latent space and use it to carry over? So this output here would be dynamic length, which is great in most situations because, it's very hard to have a fixed length for all sorts of general problems. Like you kind of still need to map to something. Like sometimes you don't know how long to output. So I think dynamic length output is still better. So I call this the universal thought machine. You take in anything as input, allow external tool use and interfacing with simulation modules, planner modules, and so on, and output in both latent space and language space. So the latent space can be used to condition the next run of this like transformer so that it doesn't start from scratch. So my view is that it might be easier to adapt current transformer architectures to use the HRM style latent space than use the HRM style latent space and try to incorporate transformers multimodal stuff into it. Yep. Derek?
So my understanding of the way current reasoning language models work, at least on the pure language side, and this is from a couple of the DeepSeek papers that I've read that I've enjoyed a lot. I'll try to see if I can find the one I'm talking about. There's a lot of correlation in studies they did on the reasoning part of the neural network, or the language model, I should say. And what they found in correlation is that what it outputs in language as reasoning is very dissociated from how it reasons in its latent space. And there's like a bunch of like tools that they use to like study the latent reasoning part of the neural network and the activation functions and all of that. And what they found is that the reason it reasons the way it does in language is because of how it's conditioned during the reinforcement learning. It gets punished and it gets pushed towards tokenizing its thoughts into actual word tokens, and it gets pushed towards explaining everything it's doing. But that part is actually very dissociated from the internal reasoning that the model does in its latent space to actually come up with the solutions that it does for reasoning. So its reasoning and its language explanation, you could call it, are very dissociated from each other. And I find that interesting in your explanation and your idea of trying to make language and lane space be two kind of like dynamic spaces that can be outputted side by side. But my understanding of language models is that they already have a lane space to them. Their issue is that that lane space may or may not be either may or may not be fully construed as an output. The language reasoning that we all analyze may not be the best representation of the latent reasoning that it's doing. And maybe that the language reasoning is suboptimal and disconnected from the true reasoning in the latent space of the language model, from all of the chain of thought reasoning and RL it goes through. And maybe that the two are so disconnected that it's unreliable as a representation of the latent reasoning. But I wanted to know what your thoughts were on that issue, and if your ideas for the training and the implementing HRM as a training idea could be implemented to perhaps problem solve that issue to some degree.
Yeah. So I do think what you said makes sense. Like the language and latent space might be fighting for the same representation, and the latent space may not be as expressive as language in terms of conveying information to us, but the language may also not be able to take in the representation for the latent space. So it's like if you would output two different outputs, there will be some competition in terms of gradient flow, like what goes to language, what goes to latent space, and there might be some issues here. So what could be done to solve it is that make maybe the language, like perhaps language is not using intermediate thoughts at all. Then you don't have the human chain of thought here, but the language might be needed for the output because you want the language to tell humans like what has happened. Yeah, you might be able to get some output examples of like what has been done. In fact, the language itself might be a like you can just map latent space to language. So maybe the output can just be latent space. So I mean, the language itself is really just for us. The model doesn't need language. The model can reason in latent space as what we saw in HRM. So maybe based on what I heard from you, like maybe just output latent space. Yeah, maybe just output latent space. Everything gets mapped to latent space, and then in the end, you just have an interpreter to. Yeah, maybe that will be better. Yeah. So everything output in latent space, only the final step you map back to human language so that we can understand it.
Yeah. Yeah, I can see that. It's just that there's so many papers out there from like Meta and Anthropic, and they have all of these like latent reasoning models, the large concept model from Meta, right? There's all of these research papers covering how to convert language and multimodality into pure latent reasoning. You have I have it here in my computer. It's the where'd she go? The large language models and continuous latent space reasoning via recurrent architecture. There's another paper that's older than this paper talking about the recurrent transformer concept, where you take a single transformer block, you loop it into itself ad infinitum, and then you know do the dynamic time step learning and all that other fun stuff. There's already so many other papers covering how to do pure latent reasoning and get transformers to learn pure latent concepts and pure latent thought processing, really, kind of like the latent space of actual human like thought, and not just pure language recurrence over and over again until you kind of pick up on language syntax and language semantics. So there's already so many research papers covering all of these different approaches to latent processing and latent reasoning. I'm pretty confident that the latent part may not be the issue. As you stated earlier, like transformers have so much going for them. You don't really need to worry so much about the transformer side of things. Whatever we did here with HRM, not so hard to recreate with the transformer. Tweak some multi-headed tensions here and there, do some stacking here and there on the blocks and on the tension heads. Boom, you got some magic going. So my concern with this idea is that it sounds cool in theory. I just think it may be a bit redundant, if that makes sense. There's already a lot going.
Definitely not redundant. Is a way to highlight that latent space thinking is important, but we may not use the same architecture as what is shown in HRM, because HRM architecture is just input grid. We might use the recurrent blocks of low and high, and I think they did show quite a nice way of how to train the low and high in terms of different time steps. High get updated fewer than low. I think that kind of idea can be done in the mainstream transformers that take in arbitrary input.
Right, that's what I mean. No, the concepts can't be implemented. The separation into a separate universal thought machine, that part may be redundant. But the concepts, all of the things we already have the building blocks for it in our current research, and architectures in transformers. We just have to take the HRM concepts and infuse it into our current transformers. I don't know what that looks like. There's a lot of experimentation that needs to be done, a lot of ablation studies that needs to be done. I don't have a lot of money. I can't fund all that, but I would really like to delve deep into that and see what parts of HRM can be implemented at what levels, whether they be the architectural level or at the training level. Maybe HRM is just something that can be implemented in a training pipeline, whether it be RL, whether it be a sort of self-bootstrap, self-learning pipeline at the training level, even, or you may implement it at multiple levels.
Yeah.
There's a lot of discussion that could be done, and we could go on and on about it. But I think is we have the building blocks, is my point. We just have to find out how to implement it optimally.
I'm quite interested to implement HRM like architecture with human language input, because that would make it more generalizable, definitely.
Yeah.
So I think there's something going on here. It's just that I think as an architecture, HRM is too restrictive. I think it's too restrictive right now. Yeah, I would like to make it more general. And as you said, LMs might already be headed down that path. We just need to tweak the internal transformer architecture to be a recurrent one, and then just update the recurrent in a different way than just updating every time step. That's HRM already. So I think we have converged to the point that we can just tweak the current transformer training to make it HRM-like.
Yeah, precisely. I agree. I think the corporations have spent billions and billions of dollars on the research papers. Now we just have to do our little tweaks and implement our ideas.
But it's amazing that such a small model can get such good performance. So you think like they stripped away a lot of language, a lot of things that we commonly think that is needed in reasoning. And I think this is a very good proof of concept to show that language is not needed.
Yeah, absolutely. And it aligns with what I've always had thoughts on. I've always felt that with all these latent research papers coming out, I've always felt that what the neural network does really is that it learns the latent concepts, the high level things, the reasoning algorithms and the semantics of these complex fields of data and tokens. But it's kind of separated almost. It's almost dissociated, right? The learnings are almost dissociated from the language output, right? We train the LLMs to talk to us and to tell us what it's thinking, but what it's telling us it's thinking about, right? That's superficial, basically, to
Yeah.
what it's actually processing internally, truly, when it takes in the input.
True. So I think I quite like the architecture that we have converged together. We take away the language feedback here. We have multimodal input here. Everything gets processed in latent space, and output is in latent space also, but gets mapped back to language at the end.
Yep, it's just a map, and it's very human-like, right? I mean, that's what we humans do. I don't think to you directly, right? I don't think in my head in chain of thought, right? I do my processing. I think in my own internal world model how I think the world should be or how something might be solved. Then at the very, very end of all of that thinking, then I open my mouth and I actually tell you what I'm thinking about with language. Language is a tool. Honestly, what I just said sounds great. I mean, language should be a tool call if you really think about it, right?
We have
It should
a
just
transform latent to language to call.
yeah, just call you just call your language model, buddy. Say, hey, I just finished thinking in recurrent space. Can you just tell the human what I figured out? Yeah, it should just be a tool call. Why make it complicated? Make it clean. I like that.
Nice. I like this idea a lot. So basically, we take a look at the HRM architecture. Let me just go back to the diagram. So putting it in what we have discussed, in this HRM architecture, you have a multimodal input here. We can support like image, video, audio, and it can also support like memory retrieval because your memory can be in tokens. Your memory doesn't need to be in language. It can be in tokens. In fact, it's better because then you have multimodal memory all in the same latent space. All right, memory retrieval. And over here, you have a language conversion head, which is autoregressive. So basically, your transformer can actually take in an output that can take in an input that is a hidden vector, and then you can roll out the language step by step. So traditional RNN, traditional transformers, the attention is all you need paper, has already shown you that you can take a hidden state and roll out language. Yeah, in fact, RNNs have done this also. So it's not a difficult thing to do, to just take a snapshot of the latent space and roll out the language tokens. I think it's very possible. Does this sound good to you? I think it sounds good to me. Yeah.
Yeah, it sounds very good to me. I didn't even pick up on that in the attention paper, the rolling out the hidden state. So I'm glad you brought that up. That's very good to know.
I like it. I wouldn't have thought of this idea about you. So this is great. Yeah, let me just update this slide to reflect to reflect what we have discussed. I love what we have discussed. It's a great idea. Yeah, let me just update that. And yeah, it's very late already, but let's just spend maybe like last 5 minutes here. Can this high level, low level thinking be proposed in HRM, be done back in human language with the current chain of thought paradigm? Okay, I think yes. Okay, so this is a bit different from what I discussed. Just now we talked about like, can we use latent space to think about everything? But what if we use the high and low level thinking cycle in chain of thought? Yes, you can do hierarchical chain of thought. So like you have the first layer, interact with tools. And then once in a while, go back to planner and refine the thinking path or the strategy. So actually this is done in agentic systems already, because your agent itself, it might be nested agents. Like you have an agent under agent. So like agent Joe, so you have an agent under agents. And the top level agent has a hierarchy, has a top level chain of thought. While the low level agents has like separate tool use and everything. So your chain of thoughts can be hierarchical. And then, once in a while, the agent does 5 steps and then reports back the tool use back to the meta agent. So essentially, we have low level, high level thinking in chain of thought already. It's just not in the LM level, it's at the agent level. So I think, yes, you can do this. In fact, we have already done it. There's still some limitations though, in the sense that language may not be able to express everything. So it would be even cooler if we can do everything in latent space. All right. So next, how explainable is HRM if the thoughts are not in words? So we have talked about this. You can potentially convert a latent space into language using autoregressive token prediction. You can potentially do that. In fact, that's what Transformer is doing. Transformer is basically just outputting your next token based on your hidden state at the end. All right, so this can be done. Actually, not just hidden state at the end. I think, yeah, hidden state at the end. Yeah. So you can do this. Will HRM scale to larger input context and data sets? The thing is maybe, but it is too constrained with grid input, grid output. So you kind of need to, and also too constrained with fixed output size. So in order to scale it up, we kind of might need autoregressive prediction in the output space. But apart from that, I think it can scale. But if we scale it up, then we might as well just take the transformer architecture and modify it to make it HRM much easier than taking HRM to scale it up to transformers, to like state-of-the-art LLMs. All right, same thing. Can HRM scale to multimodal instruction-based and possibly embodied system? Yes. Okay, with some tweaks. It is possible, but it depends whether you want to go from the HRM way upwards or the upwards way and modify it. I think upwards way and modify the HRM is easier. So yeah, that's more or less my thoughts for this. Questions, comments, discussion, anyone? We have like 1 or 2 minutes to spare.
No, I think we did a lot of our discussion earlier. I think you just reiterated everything we discussed into the question section. I don't have anything else to add.
That's great. That's great. I love this paper a lot. Okay, as a conclusion, although I say that algorithms might be needed to solve things more reliably, if we look at this paper here, like graph neural networks may not be that great. Same thing for transformers or neural networks. Maybe they are not the right approach to solve things, but still, it is a general way of solving things, and it might be useful if we don't have the algorithms for it. So, in conclusion, let's conclude with this slide. I think the idea of using the low-level and high-level reasoning module, updating the high-level once in a while, helps to solve a lot of the training stability in terms of gradient updates. And the idea that you can just compare the input and outputs at every time step here to do some form of learning at every intermediate time step. That is a wonderful idea. This is a wonderful idea. We need to do this more. Okay, we can learn so much if we learn from the intermediate outputs. So in conclusion, I think these are the 2 things. Better gradient updates. So HRM has 2 main benefits. Better gradient updates. Ability to learn from intermediate states. These 2 is very useful, and I hope to see more of this in the mainstream transformer architectures. And if we can interface the HRM like architecture with tool use and everything, I think it'll be very useful, thinking in latent space and everything. So looking forward to see more users of this, and thanks so much for joining the discussion today. Yeah, it was great. Okay, bye everyone.